Okay, well, let's get started. Welcome to day 4 of the workshop. Today we'll start with Clemens Berger, talking about Goodwill's cubicle cross effects and nilpotency in semi-abelian categories. Take it away, Clemens.
Thanks, David. And also thanks to Joachim for giving me the opportunity to speak at this workshop. So I'm very glad to do that because I somehow worked with Dominic Bourne on something which is very much related to the cross effects of Eilenberg-MacLane. You have seen in the lecture of Christine, and it's somehow a good way to connect actually the cross effects of Eilenberg-MacLane to Goodwill Calculus, so to the next talk, because it is somehow a way to define cross effects in a different way, and it has some advantages. It is not necessarily easier, but it can perhaps it is more versatile. It can be applied in more contexts. So I will give a short introduction. Then I try to give you the context in which I work, so semi-abelian categories. Then I will define the cubicle cross effects. And then I will be able to define two different notions of nilpotency, an algebraic one and a more homotopical one. So as a definition, I would just perhaps stress the analogy with the usual notion of polynomial. And perhaps, so Joachim asked me whether I would know some connection between polynomial functors as initially conceived for the workshop and polynomial functors in the sense of Eilenberg-MacLane. And so I think there is not a real relationship. It is more some kind of analogy. Both make reference to the polynomials we know, which are linear combinations of monomials. And I think that perhaps the common feature of both notions of polynomial functor is that there is some interplay between co-products and products, or co-limits and limits, push-outs and pullbacks. What for me is very important is that there is a notion of degree of a polynomial, which you know very well. So if it ends in degree n, and there is also a specialization to linear functions, namely these are precisely the polynomials which preserve 0 and are of degree less than or equal to 1. And the same thing will happen with the notion of polynomial functor of Eilenberg-MacLane, and also with the one I deduce from Goodwill. So you have seen that a functor between abelian categories is of degree less than or equal to n if all cross effects of order higher than n vanish for all objects of the category. I will not go into the definition of these cross effects of Eilenberg-MacLane. In any case, what is also true is that a functor is linear, so it preserves the binary sums if it deserves 0, and if its degree is less than or equal to 1. So all cross effects, all higher cross effects vanish except the first one. So the purpose of my talk is that I want to define in a precise way the notion of degree for functors between non-additive categories. And I will use Goodwill's cubicle cross effects to do so. And I would like to relate it to nilpotency. So that's the aim of my talk. And let's just briefly review what are additive and abelian categories in order to emphasize what changes in the semi-abelian context. So you know, everyone I think knows that a category is additive when it is a pointed category, such that the canonical map from the sum to the product is invertible. So this means that actually you have what is called a byproduct, which is simultaneously a coproduct and a product. So I will, in my talk, always use the term sum for coproducts. And so this is not yet really enough to define an additive category. One also requires that for every object, the identity has an additive inverse. So if you have byproducts, then you can sum morphisms, and you want that there is endomorphisms. When you add it to the identity, it gives you 0. And an abelian category is an additive category which has kernels and co-kernels for every morphism, and such that every monomorphism is a kernel and every epimorphism is a co-kernel. So how to extend this additive context? There is some kind of intermediate notion between additive and abelian categories, namely an additive category which is idempotent complete, which means that every idempotent endomorphism has a kernel and a co-kernel. And actually, if an idempotent endomorphism has a kernel, it automatically also has a co-kernel, and vice versa. So that's the notion of idempotent complete additive category. Now there is something funny which is happening with idempotent complete additive categories, namely you can somehow define them in a different way by requiring that every split epimorphism has a kernel. Because if you have a split epimorphism, then it induces on the domain an idempotent endomorphism, and the kernel of this idempotent endomorphism will be the kernel of the split epi. And moreover, the kernel of F and the codomain add up, so and give you the domain. So X is the sum of the codomain and the kernel of F. And now, in an additive category, this will be a direct sum, but this condition that when you have a split epimorphism, that its kernel and its codomain add up to X, you can formulate it in any category with binary sums. So when you have binary sums, I will just call this condition protomodularity. And because, so this was introduced by Dominic Bourne a long time ago. And so I call a split epimorphism which has this property that the kernel and the codomain generate X, I call it protomodular. So one should be a little bit careful because there are different notions of epimorphisms, and here we need that it is a strong epimorphism, which means that it is right orthogonal to monomorphisms. So every idempotent complete additive category has this this property that split epis are protomodular. Now, I define a pointed category to be semi-additive if it has binary sums, pullbacks of split epis, and if every split epi is protomodular in this sense I just gave. So this means that an additive category is semi-additive, but actually you have some property which will be very important. When you have a semi-additive category, then you have a canonical map from the sum to the product, because the product can be seen as a split epimorphism to one of the two factors, and this gives you a map from the sum to the product, which must be a strong epi. And now you can just say that a category is additive and idempotent complete precisely when the category is semi-additive, and also it's also the dual. Because if you have those conditions, then you have that the map from the sum to the product is a strong epi and a strong mono, and this is an isomorphism. So you get the additivity of your category back. Now, why I tell all this? That's because there is a quite well-known theorem of Miles Tierney, who says that a category is abelian if and only if the category is additive and exact. So now you can just weaken this and you replace additive by semi-additive, and you get the definition of a semi-abelian category as given by Janelitz, Marquis, and Tolène. So a semi-abelian category is a semi-additive category which is also exact. So I do not have time to go into the detail what is an exact category, so I suppose that you know it more or less. The category of sets, for example, is exact, and any abelian category is exact. So it means that you have finite limits, you have a stable, strong epimonofactorization, and you have effective equivalence relations. So it has been introduced by Michael Barr, this condition, and it is, I think, a very important one which occurs in very different contexts. So what are examples of semi-abelian categories? You have groups, category of groups, category of Lie algebras, and also the category of co-commutative Hopf algebras over a field. So this is a quite recent result by Marine O'Brien and Florence Sterk and Vercruis. So you see that these are algebraic objects of quite different nature, and they all share the fact that they form semi-abelian categories. Now, each semi-abelian category has an associated abelian category, which is often called the abelian core. And the abelian core is spanned by those objects for which the commutator object is trivial. So there is a very abstract way of defining this commutator subobject. It is the image of the kernel from the sum of x with itself to the product of x with itself. So this gives you have a kernel, and the image of this kernel along the folding map gives you a subobject of x, and this is the commutator subobject. So you can check that for groups, it gives you precisely the commutator subgroup. And so when this is trivial, then the group is abelian, and you can apply the same notion to objects of any semi-abelian category. And it turns out to be the right one. So For groups, it gives you the abelian groups. For Lie algebras, it gives you what is called the abelian Lie algebras, where the bracket is trivial. And for co-commutative Hopf algebras, it gives you the bicommutative, so the commutative and co-commutative Hopf algebras as abelian objects. And you can also check that in an abelian category, so if your category is not only semi-abelian but indeed abelian, then the commutator subobject must be trivial. So that's an indication that it is the right object. And it has been introduced by several people. I will not mention them. Now I will try to define the cubicle cross effects. So these cubicle cross effects, they are defined for any functor. So I assume that I have a functor between two semi-abelian categories. And I assume that the functor is pointed, so it takes the zero object of E to the zero object of E prime. Then you can define squares or cubes of any dimension. You take two objects of your category. This defines you a square by taking the sum of them. Then you have these construction maps. When you add the identity with the zero map from x2 to the trivial object, and you have it also for x2, and you can then contract to the trivial object of E to the null object of E, and you can apply your functor f. This gives you a square in E prime. And you can do this for any number of objects. So in the next dimension, you have a cube. You take three objects. You have a sum of three objects. You can contract, and then you can apply f. I have forgotten to put f of x2. There is a f which is missing in the diagram. But this gives you a cube. And now you can, if you drop the left corner, so in the square above, you drop f of x1 plus x2, or in the cube below, you drop f of x1 plus x2 plus x3, then you get a punctured cube. And what you can do is that you can compute the limit of this punctured cube. So this is an object, and I denote this object by pf x1 xn. So this is the limit of the punctured cube. Now, because it's a punctured cube, you have a canonical arrow from the left corner to this limit. And then I define the cross effects as the kernel of this comparison map. So if you want, it is the total kernel of the cube. And then you can define the degree of the functor f in three different ways. You say that the degree of f is less than or equal to n if either all n plus 1 cubes you can form with n plus 1 objects are limit cubes. So this is equivalent to saying that the comparison map is invertible. And now, because we are in a semi-abelian category, you can prove that the comparison map is necessarily a strong epimorphism. So a strong epimorphism is invertible if and only if its kernel is trivial. But its kernel is by definition the cross effect. So this is if and only if the n plus 1 cross effect is trivial for all choice of objects x1 to xn plus 1. So to give just an idea what it means for small n, so what are functors of degree less or equal to 1? So the comparison functor goes from f of x plus x1 plus x2 to the limit of the punctured square. So I go back. So if you drop the left corner and you compute the limit of the remaining diagram, because f is pointed, you have just a limit of two maps to the point, and this is just a Cartesian product. And so the comparison map goes from f of the sum to the product of the images of f. And therefore, this map is invertible if and only if f takes sums to products. So that's the correct, somehow, generalization of Eilenberg-MacLane's notion of degree 1 or of linear functors to a non-additive context. And another thing which is interesting is that if you look at the identity functor of your category, then the identity functor is of degree less or equal to 1 if and only if x plus x2 is isomorphic to x1 cross x2. So you get back a byproduct. So this is in the semi-abelian case is precisely the case when your category is actually abelian. So the identity functor of your category is of degree less than or equal to 1 if and only if your category was actually abelian. Now I will define some objects which actually have been defined also a long time ago by Higgins, and which are very much related to these cross effects. And so now I look just at the identity functor. So for my talk, in any case, the cross effects of the identity functor are the most the relevant ones. And I just drop the notation f if f is the identity. Then you have your comparison. You have your comparison functor from the sum to the limit of the punctured cube. The kernel is the cross effect, and you have your folding map into X. Now I call X an n-folded object if the folding map factors through this limit on the right-hand corner. And you see this is equivalent to the fact that the inclusion of the cross effect in the sum, when you compose it with the folding map, then you get 0, because you have a short exact sequence on the top. And this again is equivalent to the fact that if you factorize the composite to X into an epimorphism followed by a monomorphism, then you get actually the null, the trivial object. And the object you get in this way on the left lower corner, this is what is called a Higgins commutator of length n+1. So this is just a formal definition if you want. It is, and one notes it within brackets to show that it has something to do with commutators, but so far it is not at all clear that it has. In any case, an object is called n-folded if the folding map factors through this P, and which is equivalent if the Higgins commutator of length n+1 is trivial. So, but what is also the case is that you can characterize the situation when all objects have a trivial Higgins commutator of length n+1 or are n-folded as we defined above. And this is precisely the case when the identity functor of your category is of degree less than or equal to n. So this is a nice characterization of when the identity functor is less than or equal to n. This is when all objects are n-folded or when all Higgins commutators are trivial. Higgins commutators of length bigger than n plus 1. And so this is quite nice. So it relates this notion of degree of the identity functor to some properties of certain objects of your category. But it is not really related to nilpotency so far because the definition is a very abstract one. It is just a notation which suggests that it has something to do with nilpotency. And a more natural way of defining what is an nilpotent object in a semi-abelian category is by iterated commutators, commutator objects, as I defined them before. And so this also exists in literature already for quite a while. And it has been introduced by Hooke. And so I think the natural definition of an n-nilpotent object in a semi-abelian category is that the iterated Hooke commutators of length n plus 1 vanish for all objects. So for an object, for an individual object, this means that it is n-nilpotent, and we will call a category n-nilpotent if all objects are n-nilpotent. So how this notion corresponds to the classical notion of n-nilpotence for groups and for Lie algebras. So it is the correct notion of nilpotence. And somehow to show this, perhaps the easiest way is to give yet another definition of what it means to be n-nilpotent by means of central extensions. So a central extension is a strong epimorphism such that the kernel has the property that if you compute the commutator subgroup with respect to x, then you get a trivial object, and this just means that the kernel belongs to the center of the kernel is a central object, so somehow it commutes with everything. And then you can show that an object is nilpotent in the sense of the definition of Hooke, if and only if it is an n-fold central extension of the trivial object. So the central extensions of the trivial objects are precisely the abelian objects, and if you have a double central extension, you have a two nilpotent objects, a triple central extension, you have a three nilpotent object, and so on. And with this small lemma, it is easy to show that Hooke's definition of nilpotency coincides with the classical definition of nilpotency for groups and also for the algebras. And now there is an important relationship between this classical notion of n-nilpotence and this somewhat strange notion of n-foldedness. And it's the following. Every n-folded object is n-nilpotent. So being n-folded is a stronger condition than being n-nilpotent. You can also express this by means of commutators by saying that these iterated Hooke commutators sit inside the Higgins commutators of same length. So this is the same result for a semi-abelian category. So every n-folded object is n-nilpotent. So now one can ask whether the converse is true also. And it is not in general. So there are algebraic structures where n-nilpotency does not imply n-foldedness. However, this cannot happen for groups. So for groups and for Lie algebras, the two notions coincide. So I will come back to this, but I will just give you an example where it is not true that n-foldedness equals n-nilpotency. So this happens not for n equals 1, because for n equals 1, one folded and one nilpotent is just a billion. But there is a quite nice example for an object which is two nilpotent, but not two folded. And actually it has to do something with, you have certainly with division algebras over R, you certainly know that there are not so many if you put some other conditions on it. And so you have the reals, the complex numbers, the quaternions, so, and Cayley is octaves. And now what you can do is you look at the R basis and you take just an R basis, so the canonical R basis together with the additive inverses. So in the real case, you get a group which is a two-element group. In the complex case, you get four-element cyclic group. So in the quaternionic case, you get also a group with which 8 elements, and it is easy to show that this group is two nilpotent and two folded. But one dimension, so for the octaves, you see the problem is that there is no more associativity. So you have neither commutativity, neither associativity. So, and nonetheless, if you multiply these elements together, it's stable. And actually, the structure you get is known in literature. It is a loop. It is even a special loop, which is called a Mufang loop. And you can show that this Mufang loop is two nilpotent, but it is not two-folded. So, so this is an example which shows you that the two notions are really not the same. So let me come back to nilpotency. So I will denote nil n of E, the subcategory which is spanned by the n-nilpotent objects. And as I said, the category is called n-nilpotent if all objects are therein, are n-nilpotent. And there is so this is a nice subcategory. So what does this mean? Actually, it is a reflective subcategory of E. And so there is a reflection. There is a canonical way to associate to each object of E an n-nilpotent object. But more is true. Actually, any subobject of an n-nilpotent object is n-nilpotent, and any quotient of an n-nilpotent object is also n-nilpotent. So that is what is called the Birkhoff subcategory. So for any n, nil n E is a reflexive Birkhoff subcategory of E. That is quite important and has many consequences. So there is something I think which is not so well known in literature. It should be, but with Dominic, when we tried to understand nilpotency abstractly, we discovered that actually nilpotency is also a way of measuring the distance between the sum and the product. So category, semi-abelian category is n-nilpotent if and only if for all objects x and y, the canonical map from the sum to the product is actually a n-1 fold central extension. So the bigger the nilpotency degree is, the more different sum and product are. So I find this a quite nice observation. And if you see when n is equals to 1, you get again that both are coincide. So sum and product coincide because you are in the abelian setting. Now you can construct a whole nilpotency tower. And this nilpotency tower actually is somehow analogous to the Goodwill tower of analytic functor, endofunctor. So the first Birkhoff reflection goes from E to the one nilpotent object, so to the abelian object. And this reflection is precisely abelianization. So quotienting out the commutator subgroup. But you also have relative reflections between two adjacent nilpotency indices, degrees. And this defines you a whole tower, which is there. So which ends in the trivial object, but you have so to each x you can associate its abelianization, which is I1 of x, but also its best two nilpotent approximation, which is I2 of x, and its best n nilpotent approximation, which is In of x. And all these reflections are related by canonical maps. So this defines for each object x nilpotency tower. Now you can define, so what is important is, what I have written in the lemma is that these relative Birkhoff reflections are central reflections. So this means that the kernel is a central subobject, and this means actually that it is an abelian, in particular that it is an abelian object of the category. So the kernel of these relative Birkhoff reflections are all abelian objects of your category. And so by definition, so the nth nilpotent approximation is given by dividing by hook commutators. And so the kernel is embedded in this short exact sequence. And by the 3x3 lemma, which you know quite well, I think, for abelian categories, but which is also true for semi-abelian categories, you get that this kernel, this ln of x, is actually a quotient of two iterated hook commutators. And now the following is true. You can look at the condition whether this functor ln, what is his degree. And in general, it is not true that it is of degree less than or equal to n. But if this is the case, then it's equivalent to two other conditions, namely that the identity functor of the subcategory of n nilpotent objects is itself of degree n. And this means that actually every n nilpotent object is n-folded. So this means actually that the two notions coincide, because we have already seen n-folded implies n nilpotent. So the condition that the two notions coincide is precisely the fact that these ln functors are all of degree less than or equal to n. And now there, in the special case where E is the category of groups, the direct sum of these subquotients is a Lie ring. So, and this has been proved by Lazar, I think. And actually, it has the special property that when you have a free group, the Lie ring you obtain is actually a free Lie ring. And this implies that actually the functor ln is homogeneous of degree less than or equal to n for each n. And so for the category of groups, you have all these properties, and in particular for the category of groups, there is no difference between n-foldedness and n-nilpotency. So now I will, so that is more or less what I wanted to say about the relationship between this notion of degree for a functor between semi-abelian categories. Now I will generalize quite a bit by taking into consideration homotopy. And actually Goodwill himself introduced this cubicle calculus in order to understand from a homotopical point of view endofunctors of the category of pointed topological spaces. And so what I will do here is more modest. I will try to enrich a little bit the algebraic setting so as to be able to do homotopy with my algebraic objects. So there is a very well-known procedure for doing this. This is just to look at simplicial objects in your category, because simplicial objects are geometric objects to some extent. And so the technology which allows you to do homotopy in algebraic contexts are Quill modal structures. So I do not have really time to go into any detail. But a Quill modal structure is given essentially by a class of weak equivalences. So, which means that when you have a weak equivalence between two objects, then these two objects from a homotopical point of view are identified. However, you have to be careful to how to identify it. And Quill introduced his notion of modal structure because it captures as well topological examples as well algebraic examples. So you can somehow use your topological intuition of homotopy to do homotopy theory with algebraic objects. And the means is that actually that you have also two other classes of morphisms, not only weak equivalences, but also cofibrations and fibrations. And they must be related by two weak factorization systems. So when a cofibration is also a weak equivalence, you call it a trivial cofibration. And the same for fibrations. And you want that trivial cofibrations and fibrations form a weaker factorization system, and also cofibrations versus trivial fibrations form a weak factorization system. And then the main theorem of Quill was that when you have such a setting with three classes which satisfy these axioms, then you can actually localize with respect to the weak equivalences. You can define a homotopy category where morally the objects are the objects of E up to weak equivalence. And you can do this construction staying within the same universe. So there is not some kind of very large construction of localization to do. You can even keep the same objects to do it. And so what is also good is that when you have two categories with Quill modal structures, then you have a notion of a junction which respects the modal structures. And this is nowadays called the Quill junction. And it is then a Quill equivalence if on the homotopy categories, it induces an equivalence of categories. And topological spaces and simplicial sets, they are related by such a Quill equivalence. And what is important is that the fibrations on the combinatorial side, on the simplicial side, are well understood. So these are known as Kant fibrations, and they can be defined by lifting conditions. And so what Quill also proves already in his original paper is that in seeking examples where such modal structures exist, he looks at simplicial objects in a category in a variety of algebraic objects. So in a variety of T algebras for a monad of finite rank, but you can also define it in alternative ways. So when you have a variety of algebraic objects, you look at the simplicial objects which carry this algebraic structure. And then you can, of course, forget the algebraic structures. And then you get a simplicial set. And Quill shows that if it happens that this forgetful functor takes values in fibrant simplicial sets, so simplicial sets such that the map to the terminal simplicial set is a fibration, then you can construct a canonical modal structure on these simplicial objects of your algebraic variety. And Carboni, Kelly, and Pedicchio, they show actually they characterize those algebraic varieties where this is true. And these are precisely those varieties which are called Maltsev varieties. So where a Maltsev condition is satisfied. So, and Dominic Bourne showed that actually every protomodular category is a Maltsev category. So in particular, every semi-abelian category is a Maltsev category. So if you put all this together, then you see that the simplicial objects of a semi-abelian variety, they carry a modal structure. And actually, you know very well how to define at least the weak equivalences and the fibrations. So the weak equivalents are those maps which induce a quasi-isomorphism on the so-called Moore complexes. And the fibrations are precisely the strong epimorphism. So any strong epimorphism, so pointwise strong epimorphism of simplicial objects is a fibration. And this fact that you understand fibrations in this piecewise way shows you that when you have cofibrant objects of your variety of simplicial objects, then the algebraic cross effects I have defined, actually they exist, of course they exist, but not only do they exist, but also are they homotopy invariant. This means that if you replace all these n objects by weakly equivalent fibrant, then the cross effect you compute will be weakly equivalent to the cross effect of the initial ones. So the notion of algebraic cross effect in this particular setting is homotopy invariant. And this is very precious and valuable. And this allows you to define different notions of homotopical nilpotency. So you can define a a first nilpotency degree, so I call it nil 1t, as the least integer for which this Birkhoff reflection, so which exists in each simplicial degree. So you have a Birkhoff reflection into these n nilpotent simplicial objects, and what you want is not that it is an isomorphism, but only that it is a trivial fibration. So you weaken the condition a little bit homotopically, but it makes sense. So it is a homotopically senseful notion. Now you can do the same thing. Instead of taking n nilpotency, you can do it with n-foldedness. So you just require that the folding map factors through this comparison map up to homotopy. And the third nilpotency degree is, so this I cannot explain this, you will see this in the next lecture. You can ask that x is the value of an n-excisive approximation of the identity functor of your model category. And actually it turns out that, so we have seen more or less that n nilpotency is weaker than n-foldedness. And it turns out that n-foldedness is weaker than this n-excisiveness. And so this gives you a tower of inequalities, a chain of inequalities between the different nilpotency notions. And what is very nice is that in the case of groups, so groups form a semi-abelian variety, and all three notions have already been considered in literature. The first notion is known as the Beerstein-Ghanea nilpotency. The second is known as co-category, and the third has been introduced by Biedermann and Dwyer. And so what you get this chain of inequalities between these known notions of nilpotency, of homotopical nilpotency. And actually, this kind of inequalities has already been studied by Rosona-Eldred and also by Kostoya, Scherer, and Viruel. So that's all I wanted to tell. Thank you very much for your attention.
Thanks, Clemens. Okay, are there questions?
Hi, Clemens.
Hi.
Thank you for the beautiful talk. Do you know of any examples where those inequalities are strict? I had been thinking a little bit about this, but never wrote down anything.
I think there are examples where both are strict. So, but it's a while ago that I have thought about this, so I don't remember. But so at least for the first one, I think you can find it. For the second, and yes. So where I'm not sure is for the second inequality, but the first, so the Beerstein-Ghanea nilpotency is, there are examples where it is strictly less than both of the others.
And if I may, I heard recently a talk by Corentin Vienne about co-smash associativity. This looks like it's related to your third cross effect. Do you know this?
No, I don't know.
It's someone also from Marino Grand's school and so on, and they
But it should because the co-smash product is precisely the second cross effect. So
yes, and he has some generalization to
associativity should be related to the third cross effect.
yes, yeah. Okay, yeah, that was really interesting. Okay, thanks.
Great, thanks. Other questions? If not, we can thank Clemens again and take a quick break. So let's do that. Thanks again, Clemens. Okay. Yeah, so let's take a 5-minute break. Maybe during that time, Christine can start sharing screen, and see you back in 5 minutes.
Clemens, do you mind if I share my screen over yours now?
Yes. So I have to unshare it. How do I do that? Is this okay or?
It's done now. It's taken care of. Yeah.
Sorry, Clemens, I just did it for you.
Okay.
Looks good, Christine. You want to try advancing one, or you're going to do it that way? Okay, great.
Yeah, I think I had shared the wrong thing initially, so hopefully this is okay now.
It might not be there we go. Yeah.
Yeah.
All right, well, let's start back up. We're very happy to have Christine Bauer talking to us next about categorical differentiation and Goodwill polynomials. So go ahead, Christine.
Thank you very much. So I'm Christine, and I am not used to being live streamed on YouTube. I have a 10-year-old girl in the house who's very excited about the fact that her mom is a YouTuber this morning. So I have to say hello to Isabel just for the fact that later on she'll be looking this up, and it will be proudly displayed in our house next to her science fair video, which is also on YouTube. Okay. So I'm going to talk to you about categorical differentiation and Goodwill polynomial functors, and I am in the enviable situation of being able to say that many of the things that I want to tell you about today have been discussed by other speakers at this conference. And so I will make reference to some of the other talks, but I'm also not going to assume that people have seen them all. I just it's been a very nice conference to be able to see so many relations to the things that I want to talk about today. So I'm going to start by talking about abelian functor calculus. And I'm going to start by talking about a project that was completed at one of the Women in Topology workshops by myself, Brenda Johnson, Christina Osborne, Emily Reel, and Amelia Tebby. And affectionately, this project is known as BJORT, in case I manage to say that later. And what I'm going to tell you is how abelian functor calculus fits into an abstract framework that makes analogies between classical and functor calculus explicit. In fact, the whole goal of my talk is to explain to you how the polynomial functor calculi that are used in algebraic topology are actually explicitly examples of calculus. In part one, we'll talk about abelian functor calculus. All right. So let me start by making a category of categories. So abcat is going to be the category of abelian categories and functors between them. Strictly speaking, this should be a two category, but I'm not going to think about the two categorical aspects. I really just want my objects to be abelian categories and my morphisms to be functors, all functors. And I'm going to here think about functors which are homologically degree n, where degree n is thought of in the sense of Christine Vespa's talks, the Eilenberg-MacLean cross effects detect degree. So let me say a few more things about what's going on here. So first of all, Clemens very nicely just defined abelian categories for us. So for my purposes, what I care about for abelian categories is that they have the Hom sets are abelian groups. I'm going to use the fact that every such category has a zero object. And the part of the definition that I'm not explicitly mentioning is that the kernel and the co-kernel are well behaved in abelian categories. This allows for certain splittings, which I'll be using implicitly. So to say that something is homologically degree n is going to use the Eilenberg-MacLean notion of cross effects, which we've been hearing about from Christine Vespa this week. So let me just remind you that the first few cross effects are defined as follows. So given a functor f from an abelian category A to an abelian category B, then f of x is isomorphic to, well, the zero object splits off. The value of f at zero splits off, and what's left over is the first cross effect. So that the first cross effect is detecting the failure of f to be reduced. The second cross effect can be defined after you've defined the first one by looking at what happens to f on direct sums. I'm in an abelian category, so I have biproducts. And so this both x and y, the value of the first cross effect at x and the value of the first cross effect at y split off. I'm taking the first cross effect so that I have a reduced functor with which to do this, and I can ignore what happens to 0. What's left over is the second cross effect, so that the second cross effect detects the failure of f to be additive. And then I'll just note that there are higher cross effects, which are defined recursively. And I'll just say that these were defined by Annenberg-MacLean. I'm not going to need them in this talk. But these have been defined in several talks before. So in this conference, I feel that one has to introduce himself again in terms of what kind of polynomial functor are you? So my polynomial functors are polynomial functors which are homologically degree n, meaning that in abelian functor calculus, a functor is degree n if its n plus first cross effect is not necessarily equal to 0, but contractible. So here I'm imagining that I have a functor that takes values in chain complexes, and I will force many of my functors to take values in chain complexes. So this notion of being contractible is the same thing as being pointwise chain homotopic to 0. Okay. Okay, so as mentioned in Brenda Johnson's talk yesterday, there's a Taylor series-like tower of approximations. Let me just make sure that I can show the reference on the bottom. I see that I'm going to have a little trouble showing the whole slide, so I will just make sure to slide up at the appropriate time. So this is a Taylor series-like tower of approximations where Pnf is going to be a degree n polynomial functor, and it is the closest polynomial functor to the original functor f, meaning it satisfies a universal property. And I will just remind you of how this comes about. So from Brenda Johnson's talk, there's an adjoint pair of functors. So on the one hand, I will look at functors from an abelian category A to an abelian category B of a single variable. On the other hand, I'll look at functors that take n entries. So these are functors from A to the n into B. The cross effect takes a functor of a single variable and produces a functor of n variables, and it has an adjoint, which is given by precomposing with the diagonal. And Pnf so I'm going to call the resulting comonad on functors from A to B. I'll just for shorthand call that Cn. So that just means do the cross effects followed by the diagonal. And Pnf is the bar construction associated to this comonad. Explicitly, I can make this a chain complex where I just iterate. I continue to take the comonad. I should apply this to F. And the differentials are given by the unit of that comonad. Okay. So as Brenda mentioned, and I'll just reiterate this, Pnf is the closest degree n functor to f, meaning that if I have any other degree n functor and a natural transformation from f to that degree n functor, it will factor through p and f. That's the universal property. Okay, so this notion of functor calculus was established by Brenda Johnson and Randy McCarthy in a paper called Deriving Calculus with Cotriples that appeared in 2003. This is the abelian calculus version of what has been used in algebraic topology to study degree n functors in homotopy theory. I will talk about Goodwill's calculus a little bit later. My timeline is backwards. Goodwill's calculus preceded the Deriving Calculus with Cotriples paper. They're strongly related. So let me say a little bit about that relationship now. So for this Taylor series of approximations, a polynomial degree n approximations to a functor f, in some cases, this notion of degree n is the same, exactly the same as Goodwill's notion of n excisive, which Clemens was just talking about. So in particular, if f commutes with realizations, and if you're in a setting where this makes sense, these are the same. This isn't the subject of my talk. I just wanted to mention it. And in fact, I'm mentioning it again because Brenda Johnson talked about this result yesterday. So this idea of being homologically degree n, where degree n is detected by the Eilenberg-MacLane cross effects, is the same thing as being n excisive in special cases. So there is a relationship between these two, but I'm not going to go through that in such detail in this talk, because the goal of my talk is actually to talk about why this is appropriately called calculus. Okay, so one more thing about this Taylor series before I move on. So one thing that I will want to look at is not just the polynomials that are in the Taylor series, but in fact, the difference between the two of them. So let DNF denote the fiber of the map Qn, which is the map from the nth polynomial approximation to the n-1st polynomial approximation. In the context of my functors being functors from an abelian category to chain complexes of another abelian category, I showed you the construction a moment ago of what PNF looks like, and it will land in chain complexes. So this is a mapping cone construction, or it's a shifted mapping cone. So this is a very familiar construction. And in this case, this functor DNF is homogeneous of degree n. Meaning that, first of all, it's degree n. And secondly, DNF itself has no lower degree polynomial parts. In other words, the kth polynomial approximation of DNF is acyclic when k is smaller than n. I will particularly want to look at D1F. D1 has the property that it is both additive and reduced. Functors which are both additive and reduced, I'll call linear. Okay. Great. In the Deriving Calculus with Cotriples paper, the derivative is made explicit through the notion of being a directional derivative. So if I just start with functions of a real variable or several real variables, the directional derivative is given by taking the limit as t goes to 0, 1 over t, f of x plus tv minus f of x. So this is familiar. We teach our calculus, our undergraduate students about directional derivatives, and I'm not doing anything different right now. The analog of that in abelian categories, first of all, there's a nice strong analogy with that formula by using the linearization functor. So I can take my my f of x plus tv will be replaced with f of x plus v, where now I use the direct sum. And my difference between that and f of x is given by taking a kernel. And my limit as t goes to 0, well, that is supposed to linearize the derivative. And so I will just linearize, and I'm going to linearize in the v variable because that's what we did here as well. I was looking at what happened to the v variable when I multiplied by t in the original formula. So that's an argument that this should be rightly called the directional derivative. And now I want to use the fact that I know something about what's happening with f of x plus v. So remember, my second cross effect is trying to determine the difference between f of x plus v being equal to f of x plus f of v. So in this kernel, I can actually split off f of x, f of v, and the second cross effect. And when I take the kernel, what's left is f of v plus the second cross effect. Now, that wouldn't quite be right, except for the fact that I've linearized. Linearization respects direct sum. So a nice shorthand for this is that I can rewrite the directional derivative as the derivative of f evaluated at v. This one doesn't need the v decoration that tells me to linearize with respect to v because it only has a v, but I'll put it anyway. And so it's the sum of the linearization of f evaluated at v and the linearization of the second cross effect evaluated at v and x linearized in the v variable. Okay, and I should have written that this was not equals, but chain homotopic. I think this one's actually an isomorphism, but I've written it incorrectly, so now I'll never get it right. That's okay. Okay. So in deriving calculus with cotriples, Brenda and Randy showed that if I have composable functors, then this directional derivative satisfies a chain rule. And the form of that chain rule is that the directional derivative of f and g, I could have written this, I guess, with its variables, in the direction v and evaluated at the point x is equivalent to the directional derivative of f evaluated at the directional derivative of g in the direction v evaluated at x, and then itself evaluated at the point g of x. So when we were preparing for the Women in Topology conference, Brenda Johnson conjectured that this might be the same, that this chain rule might lead to a higher order chain rule, which looked formally the same as one that we had seen in a paper of Huang, Mercanto-Canini, and Young. So in regular calculus of several variables, there's a higher order directional derivative, which says that and there's a chain rule which says that the higher order directional derivative of a composite f and g is the same thing as the higher order directional derivative of f evaluated at the higher order directional derivatives from 0 up through n of g. So in fact, at the Women in Topology conference, we proved that for this way of iterating the directional derivative, I'll talk about this in just a minute, you get the same higher order chain rule. So how did we iterate our directional derivative? Well, we did this by thinking about the nth order, higher order directional derivative, that's the thing on the left, as being defined recursively in terms of the n-1st directional derivative, thought of as a functor of two variables now. So my n minus first directional derivative should eat n minus 1 variables, and then I will take the derivative of that with respect to the pair of variables given by all of the directions in the first component. And in the second component, we leave off the last direction that we took, and we remember to evaluate at the point. So this is one way of recursively defining a higher order directional derivative. And just to summarize what I said before, that thing satisfies this higher order chain rule. And that looks just like a higher order chain rule that you see in regular calculus of functions. So this led us to a question. And the question is, so this down below is the paper of Hoang, Mercantic-Nini, and Young, in which you can read this for calculus of several real variables as opposed to functor calculus. The question that's implicit now is, okay, well, we have this really, really beautiful analogy now between what's happening in abelian functor calculus and what's happening in the calculus of several real variables. Why is that happening? So why does functor calculus strongly resemble regular calculus? Okay, so that takes me to the second part of my talk, which is about Cartesian differential categories, which we also heard about from Frederick on the first day of this conference. So I'm going to start from scratch and tell you a little bit about this. But let me just highlight this quote from the paper of Blut, Cockett, and Seeley, in which Cartesian differential categories are introduced, which says that over the past few centuries, one of the most fundamental concepts in all of mathematics has been differentiation. And they didn't quite say this, but I will. When something is so fundamental, it ought to be the case that it comes from something structural, which means that it's the business of category theory. So that's what they showed. And let me just review their what they did. And we'll start again with a motivating example of what really is going on now when it turns out that we look at derivatives of functions of several real variables. So in this case, I want to look at a particular category. And the particular category that I want to look at, I'll call smooth. Its objects are the natural numbers, but I should be thinking of objects as indexed by the natural numbers. I'm really thinking that the objects are the Euclidean space Rn. My morphisms are going to be the smooth maps from Rn to Rm. And in this case, we have the Jacobian playing the role of the directional derivative. So I can think about the directional derivative in the direction v at the point A, which I'm just saying to set up my notation, as being the same thing as the Jacobian of f evaluated at A, dot product with the direction v, take the evaluate at the direction v. Okay, so we've set up that notation, and then what kinds of properties, what kind of structure does this directional derivative have? So if I'm in the category smooth, the directional derivative satisfies these 7 very familiar properties. So the first thing is that the directional derivative itself is a linear operator, meaning that if I take the directional derivative of a sum of functions f and g, this is the same thing as the directional derivative of f plus the directional derivative of g. Secondly, the directional derivative is linear in the direction variable. So in other words, if I take my directional derivative and I look at the direction, a direction which is a sum of vectors v and w, this is the same thing as the sum of the directional derivatives. I am once again talking and writing at the same time, so bear with me while I manage to sort myself out. Okay. It satisfies a chain rule, and I won't write that down because the form of the chain rule is exactly the one that I showed you on the previous slides. It satisfies a nice property when I evaluate the derivative of the identity, because the Jacobian of the identity function is exactly the identity matrix. The derivative commutes with products and smooth, but I need to be a little bit careful what I mean about this. What I mean is that if I take two functions from, say, Rn1 times R, so if I start with two functions from Rn to Rm, this is a 2. Then I can take their product by just evaluating on the first n1 variables with the first function and the second n2 variables with the second function. So I can produce a function like this. I'll call this fg. So here f was a function from Rn1 to Rm1, g was a function from Rn2 to Rm2. And when I take their product, the derivative is just the derivative of f and the derivative of g in the second component. So it doesn't, this kind of product doesn't do anything. So I just want to be careful because I don't mean the product rule that we mean when we're talking about functions of a single variable to our very, very undergraduate students. The derivative of a linear function, I'm pretty sure that I meant to say here that the derivative of a linear function is in the direction v is f of v. I think that's a typo. And we also know that our mixed partial derivatives have to agree. Okay, well, these 7 familiar properties of the Jacobian and of directional derivatives are exactly the 7 properties that are needed to define what it means to be a derivative in a category in general. So I have rewritten these now. This is my notation, not Bluetkock-Seely's notation, but it is meant to look exactly like what I had on the previous slide. A Cartesian left additive category with a differential operator that takes a function f, a morphism f to a morphism nabla f this is a differential category provided that that differential operator satisfies these 7 properties, which are exactly analogous to the ones that are before. There are 2 that are a little hard to see. It's a little bit hard to see that the 6th property is the analog of saying that the derivative of a linear function is just evaluation. And it's a little bit hard to see that this one is mixed partials. So today I'll ask you to believe me that this is the case. To see this, you can actually go right back to the Jacobian and see that in fact you're inserting zeros in certain places when you do those operations, and it corresponds exactly to where Bluetkock and Seely have inserted zeros in these functions, this one and this one. Okay. So this was published in 2009 and was used in a variety of settings. So the example smooth is from their paper, but it's also been used in a variety of settings in other places in category theory and also in computer science. But it turns out that it's also relevant in homotopy theory. So the Bjort paper that I talked about before has, in addition to establishing this higher order chain rule that I showed you, we also showed that the homotopy category of abelian categories is a Cartesian differential category. So I'm not going to go through the full proof, but let me go through a few arguments as a kind of sanity check. All right, so remember that in this case, my differential operator is going to be this directional derivative, which I can write in this nice format of being the derivative of f evaluated at v, and the linearization of the second cross effect of f in the v variable. So let's check a few of the axioms. So first of all, nabla is a linear operator. This basically follows from the fact that D1 itself is a linear operator. So if I look at the directional derivative of a sum of functors f and g, well, this should be, and let's go ahead and write the variables because it makes it easier to keep track of who's getting linearized. I see that I've switched from x to a, that's okay. So this should be the same thing as d1f composed with g evaluated at v plus d1 v second cross effect f composed with g evaluated at VA. Okay, so both the linearization D1 and the cross effect preserve direct sums. So this is the same thing as d1f of v plus d1 g of v plus d1 cr2f of va plus d1 cr2g of va, because of the two properties that I said. The cross effects preserve direct sums and the linearization preserves direct sums. All right, so let's look at the second rule. So nabla f of blank a is supposed to be linear. So this should be additive and reduced in the v variable. But this is forced by the fact that what I'm really looking at is the same thing as d1 in the v variable. Remember, d1 preserves direct sums. So this is really d1 of some other functor. And d1 is the thing that makes something reduced and additive. So this will be linear in the direction variable simply because I've applied d1 in the direction variable to another functor. And then the third thing that we can put into our sanity check before I run out of room on this slide is that the chain rule holds. And that was not new. But let me write it this way just to make a point. So the chain rule here said that if I have composable functors f and g, then the directional derivative is the same thing as the directional derivative. This is just what I wrote down before. I just want to say one thing about this. The directional derivative of f evaluated at the directional derivative of g in the direction g. But note that this is not equals. It's a chain homotopy equivalence. So in fact, this results in the original paper of Johnson and McCarthy was a quasi-isomorphism. In the Bjort paper, we upgraded it to a chain homotopy equivalence. And that is why the theorem says that the homotopy category of abelian categories is a Cartesian differential category. So we did not strictly verify all of the axioms of Bluch, Kochen, and Seeley. Instead, we showed that they held up to chain homotopy equivalence, and then the theorem passes to the homotopy category. Okay. Great. So now let me say something about the case of functor calculus for the situation in which we're not working with abelian categories. So in the case of abelian categories, one of the things that we relied on very heavily was the fact that in abelian categories, we have biproducts, and we were able to split certain sequences that involved those biproducts to make it so that we could have our nice definition of cross effects working by splitting off pieces of functors that we cared about. That's why the cross effects identified things that were reduced or additive. And we used that kind of throughout the constructions that we were working with biproducts. But in the case of Goodwill's calculus of homotopy functors, one does not have biproducts anymore. So this is exactly what Clemens was talking about in his talk, and we have to replace the cross effects with something else. So both Clemens and Brenda Johnson have mentioned this, and I'm going to mention it again. But it's still the case that we're able to say that formally something that is really calculus, something that is really fundamental to calculus is happening. So I'm going to talk now about a paper that I wrote with Matthew Burke and Michael Ching that makes precise the analogy between Goodwill's calculus of functors and the differential calculus of smooth manifolds, and show you. I'm just going to briefly say what the relationship is here. Okay. All right, so let me just reiterate some things that have already been said. So now let me go back and talk about an excisive, which I mentioned at the beginning of my talk, but I want to make precise now. So for a moment, let's just work with functors of topological spaces. So here I want to take a functor f that goes from top to top. And I'm doing that for simplicity. So both Clemens and Brenda Johnson have mentioned that, in fact, I could do this for any model category or simplicial. Maybe I want to work in a simplicial model category, depending upon what I'm after. But just for the sake of simplification, we'll think about topological spaces. So the category of topological spaces has a coproduct that I'll denote by this wedge, and it has a product that we usually denote by the times symbol. This is just the wedge of two spaces, like literally join two spaces at a single point, and the product is very familiar. So a functor is excisive, or one excisive, if it takes homotopy pushout diagrams to homotopy pullback diagrams. So let me just write down an arbitrary homotopy pushout diagram. And so to be excisive means that I take this pushout, so x plus over ay is just my notation for what it means to be the pushout. And so now if I apply f, I still get a commuting diagram. But in general, it's not the case that this diagram has any special properties as far as being a pushout or a pullback. So to be one excisive tells you something nice about what happens to f of a. F of a has to be homotopy equivalent to the pullback. So I'll write that as a kind of fibered product. But again, that's just notation, my notation for the pullback diagram. Okay, now in the special case when a is a point, x plus y, that coproduct is just actually the coproduct. And I could be asking in this case what f does to coproducts. It turns out you can rephrase that by saying that being one excisive, and one of the things that being one excisive applies if f is reduced, is that f of the coproduct is just the product. So this is our analog of what it means to be additive, but we're no longer dealing with the same product and coproduct as we were before. One thing we can say about being reduced and additive is that, one thing we can say about being linear is that the functor f is now expected to take coproducts to products. Okay. Marcelo asks, is it straightforward that the Cartesian structure remains Cartesian when passing to the homotopy category? Yes. So it's maybe not straightforward. So I maybe need to be careful about making sure that I replace, when I pass to the homotopy category, I might want to replace things with things that behave nicely. So for example, in this diagram that I'm looking at now, the homotopy pullback diagrams and the homotopy pushout diagrams that I'm looking at are not strictly pushout diagrams. In order to take a homotopy pushout, I need to replace my maps and my objects by things that are cofibrant. And then I can take a strict pushout. Similarly, for a pullback, I need to replace the objects and the maps by things that are fibrant or fibrations. And then I can take a strict pullback. And so it is the case that you can use this to say that the homotopy category is again going to be Cartesian, but I might have to do some replacements in order to verify that everything works the way that it's supposed to. Up to homotopy, everything works, but it works exactly because I'm able to make these kinds of replacements. Okay, sorry, that was a not very straightforward answer to that question.
Thanks a lot.
I'm sorry, I didn't hear.
Thanks a lot.
Yeah, no problem. Okay, great. Okay, so my excisive functors are ones that take homotopy pushouts to homotopy pullbacks, and there's a notion of being n-excisive, which means that I'm going to take an n-cubicle pushout diagram in which every face is a pushout, to an n-cubicle diagram in which the whole diagram is a pullback. Clemens described this. It means that if I delete the initial vertex, then the initial vertex has to be homotopy equivalent to the limit of the remainder of the diagram. I won't need to talk about n-excisive so much. I'm really going to focus just on the case of one excisive. So looking at the squares is sufficient for now. And just like in the abelian case, there is a Taylor series-like tower of approximations where P and F is somehow the best or the closest and excisive approximation to F. Similarly to the abelian case, this means that there's a universal property that tells you that any other degree or n excisive functor with a natural transformation from F has to factor through P and F. All right. Now, in the case of Goodwill calculus, there's a theorem which says that, well, remember I talked to you before about the layers, D and F. So this was obtained before by taking the fiber or the shifted mapping cone of the map Qn. So here I'm just going to take the homotopy fiber, which is a homotopy pullback diagram of the map Qn. And this has a very special format in Goodwill calculus. The layers look like some derivative dnf smashed with yes, let me evaluate this at x so that I have something that I can put here. So this one was definition. So this will be dnf evaluated at x. And then I take the smash product with x smashed with itself n times. And I divide out by the action of the symmetric group. So implicit in here is that I'm assuming that there is an action of the symmetric group on the left-hand side. The action of the symmetric group on the right-hand side is just given by permuting the factors. And I take the homotopy orbits of that construction, which I just denote by the same way we would do if this was a tensor product, by dividing out by the action of sigma n. Okay, but this looks an awful lot like the homogeneous part of a Taylor series now. The first part really does look like some nth derivative. The second part really does look like the polynomial x to the n. And I think it was Christine that mentioned earlier that dividing out by an action of a symmetric group is an awful lot like dividing by n factorial, which is of course the order of the symmetric group. So here I also see this really strong analogy between what's happening for the Taylor series of functors and calculus of a real variable. And so I can ask the same question. Why does Goodwill's calculus behave so much like regular calculus? Okay, well, one way that I might think about this, given what happened with abelian functor calculus, is I might ask, is there some bigger category that contains my functors between topological spaces, but maybe also all my other homotopy functors, which is a Cartesian differential category? The answer to that is probably not in the generality that I just said it, because of the fact that we don't have that nice notion of byproducts. We really lose the ability to directly say that there is a Cartesian differential category. But there is a notion of differentiation, which is more general than Cartesian differential categories, which does work. So I'm only just going to have a chance to mention this at the end. The thing that I want to look at are called tangent categories. And these were invented by Grandis some time ago. But I'm thinking of the reinvention that was more recently published by Robin Cockett and Jeff Crotwell. So this is in a paper called Differential Structure, Tangent Structure, and SDG, which applied in applied categorical structures in 2014. So basically what they say is that there is a categorical notion of a tangent category, which behaves very much like the tangent bundle of a manifold. And so what should that come with? Well, it should come with some kind of projection. So for each one of these, I've written it as a natural transformation, but we should be thinking of this evaluated at an object of the category, maybe called M to make its resemblance to a manifold really clear. And when evaluated at an object of the category, then this projection is just the projection of the tangent bundle back to the base manifold. It also has to have a zero section. The fibers of the tangent space should act like commutative monoids. If I take the tangent bundle of the tangent bundle, there should be a canonical flip, just like what we see in geometry. And I should have a vertical lift, which takes me from the tangent bundle to the tangent bundle of the tangent bundle. So these 5 maps are required to exist to be a tangent category, and then a whole lot of structure, which I'm not going to show you. There are a lot of diagrams that have to commute, and enough of them that I don't want to show you in a slide and a talk in the last 5 minutes. But suffice it to say that this is supposed to make it look like this structure behaves exactly like what is familiar to us from differential topology or differential geometry. Okay, so I guess all I said about this is that these natural transformations make Tm into a bundle of commutative monoids over M, and that this strongly resembles the tangent space of a manifold. Okay. So this is the place where it turns out that I can say something about Goodwill Calculus. Now, to do this, I have to take into account homotopy theory. So remember that when I looked at Cartesian differential categories with Brenda and Christina and Amelia and Emily, we did not show that the axioms held strictly. We showed that the axioms defining a Cartesian differential category held up to homotopy equivalence. In this case, we have not tried to do that to these to this large amount of structure that defines a tangent category, because showing that these things would hold only up to homotopy equivalence and that all of the resulting diagrams commute involved so many coherences that wasn't quite the way to do it. Instead, we took another approach using infinity categories. So an infinity category is a way of doing homotopy theory, which allows us to count all of those coherences so that when things are homotopy equivalent, I can take into account all of the coherences implied by that up through higher dimensions. Again, I'm not really going to say what this is in this talk. This is just a little bit of an advertisement or a preview. But I can take an infinity category of infinity categories. And within that, I want to look at the infinity categories where the functors have some special properties. I want to look at the functors that preserve sequential colimits. And what Michael and Matthew and I showed was that, in fact, that thing is a tangent infinity category. So the version of tangent category appropriate to homotopy theory. And more importantly, the tangent functor is given exactly by excisive functors. So if I want to show that that C is my infinity category, which is acting like a manifold, I need to tell you what the tangent bundle is for the category C. The tangent bundle is given by the excisive functors from the category of, essentially the category of finite simplicial sets into the category C. Okay, so this is hard to write down without telling you all of the things that are in here, but it would be a second talk for me to explain it all. And what I want to say is just what the moral of the story is. The moral of the story is that in abelian functor calculus, there is a notion of differentiation, which is very strongly a categorical notion of differentiation. And in Goodwill's functor calculus, there is a notion of differentiation given by thinking about things as being excisive, which is very strongly a notion of differentiation. So here I've shown that the tangent bundle is given by the excisive functors, but that means that the excisive functors are exactly acting like tangent vectors to a manifold. That means that we can think about them as being something that is trying to give differentiation. Okay, that's it. Thank you very much for your attention. Here's a few of my references and I think that there may be even more that were in the footnotes of this talk.
Great, thanks, Christine. Okay, are there questions?
I have a question if...
Sure, go ahead.
Yes, okay. Thank you very much for the very nice talk. I learned a lot. So it is also, my question is related to a question I asked in Brendan Johnson's talk, which is the direction of this map going from F to the tower. So I know, and also connected to what you mentioned about the group action, which I know happens in the species world. So if I take, say, a functor from set to set, and now I restrict it to a functor from finite set to set, then I take the left-hand extension, that will give me an analytic functor in the sense of Joyal, which has an exponential power series version. And because it's a left-hand extension, the direction of this mediating map will go from that analytic functor to F. Here, you get the same kind of analytic functor flavor with this exponential kind of power series, but your maps are going in the other way. So I don't know why this is happening, or I cannot kind of get the two things together. And it feels that they should be together because I also know that in the by category of generalized species of structures, we have a full differential calculus, in fact, a full differential category, even with exponentials or Cartesian closed structures. So I don't know if there is something you can say about it. I'm really wondering, I don't know.
Okay, so there's two things I can say about this. So one is that there is another notion of calculus which flips all of the maps in this diagram around. So the notion that we're using uses the cross effects, and the cross effects are defined in the end by showing that something is a pullback diagram. That's kind of why F wants to map into it. So I'll write that down more explicitly in a moment. But there's also a notion of a co-cross effect. A co-cross effect would want to take a homotopy pullback diagram to a homotopy pushout diagram, and that wants to map into F because coproducts want to have the property that they want to map into things. And so from the notion of a co-cross effect, I can make a completely dual tower. And this was recorded in some papers, in a paper of Randall McCarthy, whose name is escaping me right now. It might be called something like dual calculus towers, I forget. But in that case, it turns out that the calculus tower wants to map into F. So it may be the case that the example that you have in mind, maybe, I'm not sure, but it may be more closely related to the dual calculus tower than the calculus tower. Okay, so now let me say why it is that, that F wants to map into P1F. So maybe I should have done this for the abelian case where I actually showed you what P1F was equal to, but I think that I can do this really briefly. So I have this, just like I had in the case of abelian functor calculus, I have this comonad that's acting on functors from top to top. So I have an adjoint pair here, one of which is given by the nth cross effect. So I'll make this an n instead of the other, and one of them which is given by the diagonal. And Brenda has put the name of that paper that I was trying to remember about dual calculus here.
Great.
Thanks. Okay, so I get a comonad acting here, and then just as before, my PNF is defined to be, well, now it's going to be a homotopy fiber. Gosh, homotopy fiber, homotopy cofiber. I'm having trouble remembering how to do this. Homotopy fiber of that comonad iterated as a geometric construction now. So now this will form a simplicial set. And I take the, yeah, so this should have been a cofiber. Okay, thanks. I'm sorry that I'm choking over this. I just wasn't quite ready to do it. Okay, so I use this to make a simplicial construction, and that thing wants to map into F. So when I take the cofiber, that means that what I end up getting is an exact sequence, which has essentially the cross effects here. It has F in the middle, and it has P and F at the end of that exact sequence. So that's where the map is coming from. It's coming from the fact that the way in which you construct a degree n functor is that you take the failure of F to be degree n, which is embodied in these n plus first cross effects. They themselves want to map into F because of the fact that they were, of the way that they were constructed. And when you kill them off, that means that you're taking a quotient. So F maps into P and F because it is basically a quotient construction. So I hope that that helps to answer the question a little bit about why it is that the direction of the map goes that way. And like I said, I'm not sure about the situation that you're asking about with finite sets. It's possible that I should be, if I'm trying to think about that in the analogy, maybe I should be thinking about this dual calculus instead. Okay, thanks. Sorry, it took so long to answer the question.
Great, thank you. Thanks, Marcelo. I have a question. I was wondering, so you want to get these Taylor-like towers, and then in one case you use CDCs, and in the other case you use tangent categories. Do both of those have Taylor towers automatically? And if not, or if so, or whichever one, is there some common denominator, quote unquote, that is what you're really using to get what you actually want? Or maybe what you want is this explanation, but like, what is the true explanation for the thing you're finding?
Right. So let me say a couple of things. So first of all, in the Cocken and Crutwell presentation of tangent categories, one of the things they say is that a tangent category kind of contains a CDC. The tangent spaces themselves inside of the tangent bundles should form a CDC. In the case of the infinity categories, the tangent bundles form a Cartesian differential category if it turns out that you're looking at stable functors. So we have to be in that situation where it turned out we had byproducts in order to recover the CDC. So it's sufficient, I think, for your question for us to think about the Cartesian differential categories, because the idea of kind of really formalizing differentiation is, even in tangent categories, is to move into one of those. Now, there is a way in a Cartesian differential category to think about what a homogeneous degree n thing might be just by taking iterated derivatives. And then I could add those up to get something that looks like a Taylor series. So there is a way to do it. The thing is that when you do that, when you just add up homogeneous pieces, you're assuming that these towers split. And the tower that I have in front of you has extension data. It won't necessarily split. So I do understand how to get back the, from a Cartesian differential category, I do understand how to get back the layers of the Taylor tower. I don't know exactly what to say about the nth terms of the Taylor tower. In the tangent infinity paper, we do actually talk about this a bit because there's a way of thinking about n jets, which again is a notion from differential geometry, to get back the PNs, the nth polynomial approximation. And so we do the analog of that in the tangent infinity case, but I don't know what to do if I'm just in a CDC.
Cool, great, thanks a lot.
Thank you.
So if there are no more questions, which I don't see any, then let's thank the speaker again. Thanks, Christine.
Thank you.
And we'll move to our next talk, which I think is Sean.
Okay.
Looks good. We can hear a bit of clicking, but maybe that
will stop, hopefully.
Okay. All right. Well, let's just get started. So next we have Sean Moss talking about dependent products of polynomials. Please, Sean.
Great. Thanks. Thanks very much for inviting me to talk. Okay. Let me start by sort of introducing myself and how I came to think about something which is related to polynomials. So the point of departure is that Tamara von Glen in 2014 wrote a PhD thesis in which she observed that there is an operation on display map categories, which we can notate as poly, right? In the case where our display map category is the category of sets together with all morphisms, then this just is what I would, before this week, I would have called it the usual polynomial functors category. I mean, polynomial functors from set to set, okay? So that generalizes this, and it turns polynomial functors from set to set into a model of type theory, okay? When I say model of type theory, I'm always meaning something quite weak. So I just mean a display map category, which was formulated by Paul Taylor, our next speaker. So that's a category with a distinguished class of morphisms, where those morphisms always have pullbacks, and pullbacks of those morphisms are again in the class. Okay, so more concretely, to say that polynomial functors form a model of type theory, in this case, it means that they have slightly more local exponentials than they have just because they form a Cartesian closed category. So it was already known that poly was a Cartesian closed category. And it was also known that it was not locally Cartesian closed, but Tamara showed that it was a little bit locally Cartesian closed. Okay, that's very much simplifying what it was that was shown. And I'm not talking about identity types or anything like that, only really the sigma and pi constructors from type theory. Okay, so two significant observations to make on that are that because there is an analogy between dialectica categories and polynomials, under which you can think of dialectica categories as being objects of polynomials which are refined by a predicate. So in terms of positions and directions, you say an object in the dialectica category is a polynomial together with a predicate on the set of directions. Okay, I'll come back to that in more detail a bit later. But the interesting thing to study in dialectic categories is whether they have tenses and products and whether these are monoidal closed or not. Okay, so there is potential from this to consider sort of local exponentials in a dialectic category. Although because polynomials are not locally Cartesian closed, we don't expect the dialectic category to be. It is still a little bit locally Cartesian closed. Okay, and the second point is that this is a model of dependent types which arises from freely adding sums and products. So the question Martin Hyland posed to me when I was doing my PhD is, can we extend Tamara's observations to the dialectica categories that come from the other variants of Gödel's dialectica interpretation? Okay, and so that became my thesis and also a paper I wrote together with Tamara. I'm going to steadily explain a lot of the words I just said, and I'll avoid explaining some of them, but hopefully you'll still get something out of it. So I can't explain fibrations to everyone, so I'm going to kind of not talk about fibrations very much. I won't define them. I'll mention them in a couple of places. So if you know about them, then hopefully you'll get something out of my extra explanations. Okay. So here's the outline, roughly 4 parts. So in order to say something about, in order to talk about the phenomena that arise in dialectic categories, I need to work with a slight generalization of polynomials. So I want to make 2 clarifications about the title of this first section. Firstly, whenever I write Blackboard bold C, I just mean a category. I do not mean complex numbers or anything like that. That's just my name for a category, often a small category, but often not a small category. Okay, the second is, I'm never really going to talk about polynomial functors as functors. To me, polynomials are analytic objects given in a free sum product completion of something. Okay, so the ordinary poly category is the free sum and product completion of the category which has one object and one morphism. And as a sort of reasonable compromise on the way to generalizing this to what we need for dialectic categories, I've settled on explaining sigma pi of an arbitrary category. Okay, so this should be quite a leisurely introduction to the category poly, except there's a little extra parameter there because you can vary the underlying category C. Okay. Really, we want to generalize polynomials even more, but I'd rather not go through all the details of doing that. So I will only say a few words on it. Okay. So with that defined, we know that the category poly has quite a few tensors and monodal structures and monodal closed structures on it. So I'll say a bit about how you have those for sigma pi c rather than just poly, which is sigma pi 1. And I'll also try to make good on the title of this talk by explaining which local exponentials exist in poly and what we can say slightly more generally for sigma pi c. Okay. Following that, I'll try to give you a crash course on dialectical categories. It will be a very brief one, just to explain why we might want to generalize polynomials even further. In particular, why the so-called variants of Gödel's dialectic interpretation suggest new variations on the sort of classic polynomial category. And then finally, I'll say a little bit about just one of those possible generalizations, the one that corresponds to the variant of Gödel's dialectica due to Diller and Nahm. Okay. So section 1, polynomials in C. So first of all, ordinary polynomials. I'm going to steal this notation where the object little y is defined to be the identity functor from set to set, which happens to be the same as the representable on the terminal object of set. Okay, and then poly is defined to be, or can be defined to be, the closure of this one object subcategory under both sums and products using functors from set to set as an ambient category. Now, we might want to do this because we like functors from set to set, and we like to have a nice way to construct new functors set to set. But the point of view that I'll take is that actually we only do this because this is a way, this gives us a model of the free sum and product completion of an arbitrary starting category. In this case, the category with just one object and one morphism. So this did come up earlier in the week. This is the FAM construction, or the free sum completion of a category. So I won't need to spend too much time on it. So these first two boxes give you a very concrete description of what sigma of C is, sigma of C being my notation, what is also called FAM of C. So the objects of sigma of C are given by a set I and an I-indexed family of objects of C, which I will write variously as set I downstairs, and then living upstairs is the family of objects, or I'll just write it as a formal sum of the C I's. Okay, and then morphisms are so equivalence classes of diagrams that look like this. Sorry, just diagrams that look like this. And you can alternatively define it in terms of the universal property. So it's the free category with a functor from C into it, which has sums. Okay, or you can define it as I did in the previous slide. Take the pre-sheaf category on C and close the representables under sums. Okay, if we can freely add sums, then we can freely add products, because we just freely add sums to the opposite category of C, and that's how we freely add products. So the objects of the free product completion are exactly the same as the objects of the free sum completion, except sometimes I'll write them as a formal product rather than a formal sum. And of course the morphisms change. Now this arrow goes backwards. And what we're really interested in is doing both of these. So sigma or pi of C, adding products and then adding sums. Okay, objects are bundles of objects in C. So formally, it's a formal expression, a sum of products of objects of C. And a morphism, you can see it looks quite a lot like a morphism in poly, except there's some stuff going on upstairs here. So the C's and the D's have to meet in the middle. So you re-index the bundles of objects. So they now live over the same thing in the middle, and then you have a family of maps going across. Okay. So some basic examples. If I start with the one object category, one object and one morphism category, and take its free sum completion, that's just sets. If I take the free product completion, that's just set op. And if I do sigma pi 1, that's poly, as I've already said. Okay. So first interesting example, or first new example, if instead of taking the one object category, I take the 2-element total order, so an element has an object bottom and top, and there's an arrow from bottom to top, then this is, I'm putting in quotes, the dependently typed dialectica category. So the usual classic dialectica category is a subcategory of this. I'll tell you which one it is later. But so by generalizing poly to sigma pi of C instead of sigma pi of 1, we have at least one thing that is arguably a dialectica category. So the objects in this you can think of as, so there is a functor from this sigma pi 2 down to sigma pi 1. So every object has a polynomial underlying it. And then the fact that it's a formal sum of products of sort of objects in here means it's like a polynomial with a predicate on the set, on the total space of the bundle. Okay. And two more cute examples. If you have a discrete category I, so just a set, and you take free sum completion of it, that's set to the I. And if you take sigma pi of a set other than just 1, okay, including 1, then that's equivalent to the category of multivariable polynomial functors set to the I to set. Okay, so I know this was mentioned last year in Richard Garner's excellent tutorial series on polynomials and categories with pullbacks. So if C has products, then the sum completion of C has products as well, because you sort of imagine this thing on the left is it's a product of bracketed sums. So you have to do a little bit of construction in set to calculate the set of choice functions. How many ways are there to choose one element, one summoned in each of the bracketed factors of this expression here? Well, it's given by this in set. So you can sum over those and then take the product of the various choices you made. So this always exists, assuming that C has products, and therefore it satisfies the universal property that the thing on the left should have. Okay, so that gives you the product in sigma C. Okay, and it's also easy to check that the inclusion of C into sigma of C preserves the products that existed in C to begin with. And you can then check by hand if you look at the diagrams that express the universal property of sigma C. But this means that sigma pi of C is the simultaneous free sum and product completion of C. So it's not just freely add sums after freely adding products, but it's the universal way of mapping C into a category which has both sums and products. And so the deep thing going on in the background is that there's actually a distributive law between two monads. Right, but we don't need to go into that. So there's a question in the chat, and I believe that the free category with products and what? Okay, well, I can't answer that right now. Sorry. Hopefully someone else can answer that. If I'm wrong about this, then that doesn't actually really affect too much. So anyway. Okay, so here's the generalization we really wanted, but which I don't want to talk about too much. So instead of starting with a category, just a category, we're going to make more explicit the dependence on sets. So when I've been talking about free sums and products indexed by sets, I mean, so there's a dependence on the set there, and I can replace that with a different category, whose objects are like the arities that I want to take sums and products over. So replacing sets by a category B, instead of having just an ordinary set category, I have a fibration over B. So this is a bit like having, a bit like saying I have a category which corresponds to the thing that lives over the terminal object in B. And as well as having that, I've also got specified collections of permitted bundles, right? Rather than saying every set indexed family of objects is a valid input to a product, then I specify in advance which ones are valid, okay? And furthermore, I have a category of display maps, F. So B comes equipped with some display maps. So in the basic case, you take all maps in set, and you can think of this as saying, I want to restrict the sizes of products and sums that I'm allowed to take. So, for example, I could take all morphisms in set that have finite fibers, and then I'd only be thinking of freely adding finite sums and products. Okay, so given this input data, there's then a way to freely complete that fibration with quantifiers, so that it now has F sums and F products, and the construction of sigma F is quite nice. It's so this should be a formal sum of things in an object lying over an object of B should be something that arose from summing along one of the display maps in F. So hence the pullback. To get pi, you would just use the fibration version of the opposite category construction. Right. So to summarize, sigma pi c given by freely adding sums and products and then sums. Poly is sigma pi of 1. The vibrational setting is useful for the flexibility it gives. So for example, controlling the sizes of the sums and products that are added. And secondly, looking at non-standard notions of bundles of objects, both on the input and output level. So perhaps I only want to input like bundles that are somehow homogeneous or that are computably enumerated. And because the vibrational version of the construction outputs a vibration as well, that means whatever notion of polynomial comes out also comes with a notion of bundle. Okay. Now, poly comes with quite a few tensors, so I'll explore a bit how we have a similar arrangement in sigma pi of c. So in the case where c is small, let's just look at sigma c first. Sigma c is a subcategory of the presheaves, and as came up earlier in the week, if you have a monodal product on C, which I'll take to be symmetric for simplicity, then the day convolution construction gives you a monodal product on the presheaf category. Okay, and the only important thing to note is not the formula, but that it's given by forcing the tensor to preserve colimits on both sides. Right. Okay, so in the case of sigma of C, that's just preserving co-products on both sides. So if it turns out that the day tensor of a coproduct with a coproduct is again a coproduct of representables. So so yeah, we have this. So we get a tensor on sigma of C. This doesn't actually depend on C being small. Even in the presheaf case, it doesn't depend on C being small as long as we mean small presheaf instead. But in the case where C is small, then the day tensor necessarily has necessarily closed, has an exponential in presheaves. Okay, but in that case, there's no need for it to necessarily have an exponential in sigma of C. Okay, but we'll explore some conditions under which it does. Okay. So Okay, when we're mainly interested in sigma pi of C, so let's look at two tensors that you can have on sigma pi of C. First of all, pi of C has products, so it has binary products, so it's Cartesian monoidal. Right, so the day convolution lifts that to the actual Cartesian product on sigma pi of C. And secondly, if C itself is monoidal, then we can just do the day convolution trick twice. Okay, once we say preserve coproducts until there are no coproducts left, and now preserve products until there are none left. That's this. Okay, so let's think about when there are exponentials to the day tensor products. So we can make some simplifications by noting that C is a dense subcategory of sigma C, and it's closed under tensor. So I won't say exactly what dense means, but basically everything in sigma C is a coproduct of things in C. So C generates the whole of sigma C, as it were. The upshot is that to check that something is an exponential, it's enough to just check with little c's on the left, as it were. Okay. Right. So that simplifies checking that something is an exponential quite a lot. Okay. And now we're going to see that when sigma C has products, then it is monoidal closed for the day tensor, provided that you have the exponentials for just the representable objects. Okay, but we'll reduce the problem to something simpler again. So recall that an object is in a category E is called connected or co-prime if its covariant Hom functor preserves coproducts. So maps out of it into a coproduct essentially means that they always factor through one of the coproduct inclusions. Okay, and it's quite easy to check that the connected objects in sigma C are precisely the things that come from the underlying category. Okay. And because C is also closed under the day tensor, this means you can compute the exponential of a little c into a sum of things by computing the exponential of the c into each of the individual little things and then summing afterwards. Okay. If we make the additional assumption that sigma c is closed under products, which will be the case if C itself has products, then we can reduce the calculation of any exponential down to just an exponential between the representables. So first we take out the sum that's on the left, turns into a product. Then we take out the sum on the right because we're exponentiating by something that's connected. So as long as we can form this product and this sum of these things, then we have arbitrary exponentials in sigma C. Right. Okay, so to show that sigma C is monoidal closed, it's enough to check that we have exponentials just for the representable objects. Okay, and now the main example of interest is to check that sigma pi C is Cartesian closed. So this was shown for Poly by Altenkirk-Levy-Staton in 2010, and essentially it still works when we have sigma pi C instead of sigma pi 1. So the thing that really powers it through is that the Cartesian monoidal, the product in pi of C is free over C. So if I have a map from a binary product into a representable, then this Hom set decomposes as just the disjoint union of two Hom sets, because every map from X times Y to C factors through either the projection from this down to X or down to Y. Okay, and from that alone, and a few things I've said before, it's very easy to check that for something that lives in pi of C and something that lives in C, the Cartesian exponential y to c exists and is just given by C plus a sum of copies of the terminal object. Or this is the free terminal object that's added by pi of C. Okay, so you just have one copy of the freely added terminal for every map in pi of C from Y to C. So this bit corresponds to that, and this corresponds to that. Okay. And we're almost ready to apply the thing on the previous slide, except we just have to account for products of the the little c's on the right of an exponential. That's really easy because exponentials into a product are always given by products of the exponentials. Okay, so it's really easy to lift a tensor from C to either sigma C or sigma pi C, or in fact also to pi C. And we've seen that, it follows from everything I've said before that sigma pi C will admit a monodal closed structure, or is monodal closed for a given day tensor, as long as you have the exponentials for little c and little d coming from the base category C. Okay, and in particular, it's always Cartesian closed for C locally small. So you just need locally small so you can form this product, this sum here, but that's all. So what about local exponentials? And this gets a bit tricky in general because sigma pi of C is not guaranteed to have pullbacks in general. So we'll take a slightly easier case, just poly, which happens to have all finite limits, and that simplifies things. So I'm going to give you a list of facts about dependent products which apply when the ambient category has finite limits. Okay, so hopefully we all know a dependent product along a map F from B to A is given by a right adjoint to the pullback functor. Okay. And this is closely related to having exponentials in the slice category E over A, okay? Because if I want to construct the exponential, if I want to exponentiate by F in the slice category, I can do that by taking the pullback of something here and then piing along, okay? And conversely, if I have local function spaces, then I can construct pi f from the local function spaces. But crucially, this requires that the category itself has pullbacks other than just pullbacks along f. So here to get the exponential, to get the local exponential from the pi, we only use pullback along f. But here to get the pi from the local exponential, we need to use pullbacks along other maps, right? So this becomes a bit problematic when we don't have all pullbacks in the ambient category. But for now, assuming we do, it's fine. Okay, so this justifies the use of the word exponentiable for a map which is either has dependent products along it or which is actually an exponential object in the slice category. Okay. So another fact about exponential maps, which only applies when you have finite limits around, is that they are stable under pullback. And as a consequence, if you have a Cartesian closed category which has pullbacks, then the product predictions are exponentiable. Okay, so this was a bit fast, but it's all very standard things. And I mainly highlight it to point out that it really does require the ambient assumption of finite limits, and it's not particularly stable to changing that assumption. Okay, but we can apply it to the case of poly because it does happen to have finite limits. So yeah, the question we'll answer now is, what are the exponential maps in poly? Well, as I just said, the product projections must be exponentiable. So in particular, if f is an injection of sets from A into B, then the corresponding map of polynomials from YB to YA is exponentiable. Okay. Secondly, because every slice category has products, I can sum together things that are exponentiable in here, and that's still exponentiable. Okay, so every map that looks like has codomain y to the a and whose domain is a sum of y to the b's and connected by an injective map is exponential as well. Okay, and then more generally, if the codomain is a sum of yai, then I can rewrite the slice as a product of slices over just monic monomials. Okay, and then I can use what I know about exponential objects here to get some exponential objects here. Okay, that amounts to saying that I can always sum together exponential maps in poly and get more, and the result is an exponential map. Okay, writing this in terms of the familiar diagrams of morphisms of polynomials, it turns out that a map of polynomials, what we've shown is that if a map of polynomials has an injection here in its backwards going part, then it is exponential. And it turns out that those are precisely the exponential maps in Poly. So when Altenkirk, Levy-Staton showed that Poly was Cartesian closed, they also observed it was not locally Cartesian closed. And they gave a counterexample, a map which is not exponential. And Tamara noticed that essentially you can turn that into making this being an injection into a necessary condition, and also showed it was sufficient to be exponential. Okay. So summarize, sigma pi c is always Cartesian closed. Poly, which is sigma pi of 1, is not locally Cartesian closed, but we know exactly which maps are exponential. If you want to say something about general sigma pi c, we don't really want to just ask what are the exponential maps, because we don't expect this category to have all pullbacks. So instead, let's ask, can it be made into a display map category? So can we find a class F of morphisms in sigma pi c, which forms a class of display maps. So that means that all pullbacks of them exist and are again in F. And we probably also want all isomorphisms to be in there and to be closed under composition. Can we find a class of display maps which models pi types? So that's that says that pi f exists not as a functor from the slice to the slice, but only defined on object of the slice whose underlying map is in F. So it says we have pi f. So we have dependent products along things that live in curly F, defined on things that are in curly F, and the output is in curly F as well. So the domain of pi f is restricted from what we normally expect it to be when we're talking about exponential maps. It only has to be applied to things that are in F. Additionally, there's the constraint that the output should be in F as well. But the universal property that it has of being a right adjoint is still with respect to the entire slice category. So it's just saying that there is a partial right adjoint to pullback. Okay? We need F to be in curly F so that the pullback exists. Okay? And then pi f exists when there's a partial right adjoint to the pullback, which exists at every object of the slice which is in the class of display maps, and also such that the thing that comes out of dependent product is also in the class F. Okay. So this class of maps in Poly, given by the backwards thing being an injection, is a class of display maps. And you can generalize it to sigma pi c, and then that works, and it has pi types. So, that might not be the best thing you can say in general for specific cases of sigma pi c, but it does at least sort of lower bound the amount of local exponential you can expect to happen. Okay, so I'll try to give you a bit of intuition for why, having defined sigma pi c, we are now talking about at least the simple cases of dialectical categories, and sort of see how other things that are going on in dialectical categories suggest other things that we could be doing with just polynomials. Okay, so sigma pi 2 is the thing I said was the dependently typed dialectical category before. So I'll try and walk you through this. So the objects, we can write them as sort of a bundle of sets, so just like a normal polynomial, but now we're equipped with a predicate on the set that lives at the top, alpha. So you can either view this as a subset of A or as a map from A into truth values. Okay. And the reading is, rather than it's the sum over i's of the product over of these, it's and exists for all something. Okay. So very roughly, the what Gödel's dialectical interpretation does is that it takes propositions written in intuitionistic arithmetic and compiles them down to this form: exists for all something that doesn't have a quantifier in it. Okay, the price you pay for doing that is that the sets or the types that appear in the quantifiers get complicated. Rather than just being quantifying over natural numbers, you now have to quantify over higher functionals and things. Okay, but then the benefit turns out to be that when you interpret proofs of arithmetic into into witnesses for these existential statements, you end up only with computable functionals. Okay, so this was the original motivation for dialectica, was that it reduces the consistency of intuitionistic arithmetic into something computable whose consistency is more fundamental. Okay. Right. My way of reading a morphism in the dialectica category is to say, first of all, what does it mean to have proved one of these propositions? It means I've given an I0 in I, such that for every x in AI, this thing now holds. Okay, so that will turn out to be a morphism from a particular object in the category into this triple. It's the object which has a 1 here and a 1 here, and then the always true predicate. Okay, and then a morphism between general objects in this category are things that transform a proof of the thing on the left into a proof of the right. Okay, and the way they do that is, well, if I had a proof of this, I would have a witness, and I want to transform that into a witness of the existential here, so there must be a function. Okay, now that I've got a candidate witness for the existential, I've got to prove a for all statement. Okay, and now dialectica morphisms are required to pre-commit to making use of precisely one instantiation of the thing on the left in order to prove the thing on the right. So therefore, you have a function from which tells you which thing you've pre-committed to checking the truth of when you transform the proof of the thing on the left to the proof on the right. And then the comparison up here tells you that, well, it's just an inequality between Booleans as I've written it, but in a more sophisticated version, you would have something more intentional than just 2, and there would actually be a proof between propositions that would be part of the morphism. Right, so the classic dialectica category, as I'll call it, going back to Valerio de Paiva in 1989, is a full subcategory of the thing we've just looked at. It's the full subcategory whose objects are just product projections instead of arbitrary polynomials, but together with an arbitrary predicate on the top. So instead of taking the free sum completion of pi of 2, it's like we started with pi of 2 and then only completed under sort of homogeneous sums, right? So in dial, you can only add together things if the for all part agrees on both sides. Oops. Okay, but if it agrees, then there's just this formula for adding them together. Peter Hofstra observed that actually you can make dial look like a free sum following a free product completion if you take if you use the vibrational setting. So you take the base category B to be sets again, but instead of taking F to be all maps in set, you only take the product projections. Okay, and now this vibrational sum completion I mentioned earlier does give you back the category dial. Okay. But using the vibrational approach is an opportunity to introduce an opportunity to undo a simplification I made when I said that sigma pi of 2 is the dialectica category. Really, dialectica wants to be fibered. It wants us to have a vibration of predicates over a set rather than just saying it's these are just the extensional predicates just given by a subset of a set. I really want these to be possibly syntactic formulae. If I start with a vibration, I have the opportunity to do that. Okay. And the other thing is I also really want to get a vibration out, because if I only look at the dialectica category, then I'm only really looking at closed formulae, whereas I want the interpretation has to be, well, it's compositional. It should really also interpret open formulae as well. And as an aside, compare this with the inclusion of what I'll call lenses in poly. So polynomials whose underlying bundle is just a product projection. So those can be explained as also being a fibered sum product completion rather than just sort of being the closure in an ambient category under certain sums. So just a little bit of, I guess, background on the structure that dial has. So sigma pi 2 has products being sigma of a thing with products, and the category dial is closed under them because you can rewrite this formula here as a sum of the things that are homogeneous in the producting arity. And there's a tensor product on the category 2 given by binary meets and the top element, which by day convolution twice gives you a tensor on sigma pi 2, and turns out dial is also closed under that, right? And that's the tensor product that is usually associated with the dialectical category. So note that sigma pi of 2 has exponentials for both of these, but dial only has it for the latter. So there's always this search for a dialectical category which is Cartesian closed, and this is a way to do that. By embedding dial in this slightly bigger thing, you end up with you end up adding exponentials for the Cartesian modal structure. Okay, so just to recap, the simplest kind of dialectical category, if you ever need one, is sigma pi of 2, and the objects is we read them rather than sum of product of something, we read them as exists for all some proposition. And the original dialectic category varies from this only by requiring that the thing we universally quantify over is constant in the thing that we existentially quantify over, not allowed to vary, right? Sigma pi of 2, you can think of it as just completing dial with slightly nicer categorical properties. So instead of having weak sums, it has actual sums being a sum completion. And it's actually Cartesian closed, even though, and it's also symmetric modal closed, but dial is only symmetric modal closed. Okay. All right, but historically, the way to account for the fact that dial is not Cartesian closed is to take a co-Kleisler category of a well-chosen comonad, right, in such a way that the tensor, which is monodal closed in dial, becomes the Cartesian product, as it were. So by the fact that tensor has an exponential, it turns out you then end up sort of, you're collapsing them together. So it's a different way of getting. Okay, so I don't want to tell you what the comonads are because it's a bit complicated, but I guess the main one is the Diller-Nahm variant using the finite multisets monad, also, which is just a way of saying the free commutative monoid monad. And that's what I'm going to talk about in the very last section, last few slides. The other one is the error variant, where wherever you see finite multisets and what's coming next, you can put +1. That doesn't give you a Cartesian closed category in the end, but it does give you a weakly Cartesian closed one, and which means that its idempotent completion is Cartesian closed. Okay, so finally, I'll talk about a free sum completion of a category that has byproducts, and I'll start by explaining why this comes out of the Diller-Nahm variant. So Dill is just the name of the dialectical category, or it's the name of the co-Kleisler category of the dialectical category where you take the comonad that I didn't tell you. Okay, so the type theory part, by that I mean you forget the top row where the predicates are happening. So we're now really just sort of looking at a comonad on polynomials again. So I can actually tell you what that is. It takes a polynomial, a sum of y to the ai's, and you just put the finite multisets monad inside in the exponent here. Okay. If I take the co-Kleisler category of this, that is the same as the free sum completion of free commutative monoids, where free commutative monoids are the Kleisli category of the finite multisets monad on sets. Okay, so free commutative monoids op has byproducts. So hence, let's focus on some completion of a category with byproducts. And I want to mention independently, there's been recent work on automatic differentiation, which has used the Cartesian closed structure of these things, free sum completion of not necessarily free commutative monoids and the opposite of not necessarily free commutative monoids. And we can give a proof now that they're Cartesian closed, which is shows the connection between that and the Diller-Norm variant. This is also very easy. Assuming that our category A that has byproducts also has products, by what we said earlier, it's sufficient to show that there are exponentials of things in A by things in A. So in sigma pi of C, we use the fact that products in pi of C were free, but in A, we'll use the fact that products are sums. So a map from a product into C, well, the Hom set just factorizes like this, okay? And now it's really easy to write down what the exponent is for little b and little c coming from A. So this is the final slide. I'll just end with a thought on making the Diller-Norm dialectic category look a bit more like a free sum product completion. So let's fix a bicomplete symmetric node category V, and my main example will just be commutative monoids. So I'm going to borrow two facts from Kelly's book. If you have an ordinary category, a locally small category C, then you can get a free V category on it. So it has the same objects, and the Hom objects are given by the copowers by the original Hom set of the monodal unit. So in the case that V is commutative monoids, that just means I'm taking the free commutative monoid on the original Hom set, just freely adding commutative monoid enrichment. Okay. Secondly, there's a V enriched notion of sum completion, which is exactly the same, except I take V enriched presheaves valued in V sort of sets. Okay. So if I do this starting with 1, if I take the free commutative monoid category on that, then I get the natural numbers, not considered as a monoid in the usual way, but as a semi-ring. So the composition, so it's one object category whose morphisms are natural numbers. Composition is multiplication, and the addition on the Hom set is addition of natural numbers. Okay, free commutative monoids is actually just the free sum completion of that. Okay, it looks a bit like freely adding sums, the finite ones of which are byproducts, because if you have a commutative monoid enriched category and it has finite coproducts, then those coproducts are byproducts. Okay. So this co-Kleisli category poly sub L, which I said was the sort of types only approximation to the Diller-Norm category, you can write that as sigma, the enriched product completion of the free semi-additive category on the terminal category. Okay. Just be careful about what's going on here. I start with an ordinary category, I turn it into a V category, I product complete it as a V category, then I forget that it was a V category and sum complete it as an ordinary category. Okay, but there's a lot more to say to make this actually apply to dialectic categories, because this refinement layer of predicates that goes on top, it's not enough to just say, I want sigma pi commutative monoids of 2 turned into a commutative monoid category. That would be the wrong thing, actually. So to get back the sort of usual phenomena of Diller-Norm of dialectic categories, one has to combine this with the fibrational approach somehow. So I'll leave that unfinished thought there. thank you very much for listening.
Thanks, Sean. Are there questions?
So yes, Nathaniel Apple says that what I described was actually the free distributive category, and that's probably right. And Todd Trimble agrees. So yeah. But I think that doesn't, everything I've done is rather concrete without relying on that. So yeah.
Okay, looks like Paul has his hand raised.
I wanted to check my microphone first.
Working well?
We've had problems with my audio. So I was wondering whether there's this category is small enough in a lowercase sense to encode all its stuff so that you might have a type of types.
Which particular category? You mean?
Well, any of the categories that you're constructing of polynomials,
right.
polynomial functors. And then if you might interpret system F polymorphism.
Right. So we did look at universes in this. If you start with a universe here, can you get a universe here? And yes, you can. But I don't know if there's anything sensible to say about system F. But yeah. I don't know how to answer that.
Okay.
Okay, thanks. I was wondering, so you said that dial was not Cartesian closed, but then you add this comonad, you take the co-Kleisli, and then it is something like that. And then that comonad is like interesting from a linear logic point of view.
Yes, yes.
Whereas in the free product co-product completion, you automatically have Cartesian closure. And I was, if I remember correctly, in that slide near the end.
Right. Right. Yeah, this one. You're talking about it.
Maybe one a little later, or oh no, that's right. Yeah, but then you compare that. You kind of talk about both on the same slide at some point. Sorry. Yeah, that one. Yeah. I should have remembered the number. So is there a comparison between sigma pi 2 and dial with that comonad, that co-Kleisli? And I'm wondering about that, and whether you'd still want, and then whether you'd still want to add the comonad, like
so,
whether that linear logic fact is reflected in sigma pi 2 already, or whether
yes,
around that question, if you understand.
Maybe part of you're asking maybe whether the comonad is also on sigma pi 2, and the answer is yes. You can also that has this. I mean, there's a comonad on sigma pi 2 which restricts to the 1, which is the one you use on dial.
And does it have the same kind of linear logic interest? And is it related to the comonad you gave from multisets?
Right. So it's a refinement of that one I gave with multisets. It's just it has to say a bit more about what happens to the propositions at the top level. But on the types level, it is the same as that comonad I gave. As for linear logic, I don't really know how to answer questions about that. I think, yeah. So I think it still has the same property of collapsing the tensor and the product together, but I haven't actually thought about exactly that before. So, yeah.
Okay, thanks. Are there other questions?
I have a rather modest observation that hit me that about the sigma pi completion, which is that, and it sort of relates to linearity, which is that if you sort of get rid of linearity in the sense that if you sort of say x times x equals x, right? Sort of, so you make it multiplication of an object idempotent. Then the sigma pi thing sort of specializes to the free distributive lattice over a set or a poset, which maybe give or take sort of a truncation level, but it should basically work out, I think. That it's the same thing going on at a lower level. And in that case, of course, you have no linearity. So free distributive lattice is sort of well studied. So I think that should work. Anyway, it hit me. So thanks for the neat talk. And
Thanks. Yeah.
Note.
Great. Okay, well, if there are no other questions, let's thank Sean again. And let's take a 4-minute break or so before the next talk. Maybe Paul, if you want to try sharing screen. Looks good. Do you want to try advancing one? Okay. So we'll start in 3 minutes or so.
I also need some can you hear me?
Yep.
Right, and you can see me?
We can see you, we can hear you, we can see your slides.
Right, okay. What I was trying to do was to see the gallery. Yes, right, okay.
I'll be right back. All right. Come to the last talk of today. We have Paul Taylor talking to us about the Berry order, ideas from the 80s and stable domain theory. So please, Paul.
Okay, well, thank you to Joachim and David for inviting me to talk at this meeting, and I apologize to them for being a nuisance in several ways in the last couple of weeks. Anybody can find my slides from that web address at the bottom of the page there. So this talk is going to be about work that I did over 30 years ago, and I have actually found it difficult to remember what I was doing. I was hoping to represent Francois Lamarche's work as well, which was similar but significantly different, but he didn't want to be involved in this. I'm going at the end to be talking about Cartesian closed categories. It will be similar but different to what Francois did, and completely different to what you've just heard from Sean. So it's probably better to separate the two in your mind. Now, the main thing I'm going to talk about is Cartesian natural transformations, which have only occurred, I think, in passing during this meeting and in the last year. So that's the reason why I want to emphasize those in particular. And there's some ideas in category theory that I didn't write up properly. So younger people may want to contact me and take up some of these ideas. I need to stress that my polynomial functors may be similar to those of others, but they're going to be on categories that do not usually have terminal objects. That's a main thing to be aware of. They're called stable for reasons that I will tell you in a moment. I wish that they had been called laminated. So if we're taking this subject forward, I'd like to have a change of name. So I need to introduce my definition, and the best way to start with that seems to be the work that Yves Diaz did. So he came from commutative algebra, and he was interested in fields and integral domains and various other things in algebraic geometry. So a field is like an algebra, but it has this disjunction and this universal quantification, the essential features of which is that they're uniquely satisfied. So we either have x equals 0, or disjointly we have an inverse, and the inverse in that case is unique. And we think of the category of fields and homomorphisms as being the kind of category that I'm going to talk about, and the functors. So in this subject, what Diaz demonstrated was that we have constructions like adjunctions in universal properties like we have in ordinary algebra, but they tend to be multi-valued. This applies to forgetful functors and to colimits. They can also, these multiple values can also have automorphisms. So starting from the familiar definition of universal maps that you probably had in undergraduate algebra, with a bit of that had a bit of category theory in it. So the most familiar example is we have a set called a basis Y, and it has a free vector space, and S is the forgetful functor, the underlying set of the vector space, and it has this universal property that any function from the basis into another vector space factors through a unique linear map. Right, so we're going to generalize this. So what about field connection between integral domains and fields? So if we have a ring homomorphism from the integers into the field with 125 elements, then it has a kernel, which is necessarily the ideal generated by 5, and that has a quotient, which is the prime field with 5 elements. But we have one of these things for every possible prime characteristic, and also 0. And the collection of these things is called the Zariski spectrum. And we have a further generalization that we might ask what happens when we add groups of polynomials to a field. Well, in this case, so if we want to split the polynomial x squared plus 1, we can add the square root of -1 formally to the rationals. But there's two different ways of embedding that in another field in which this polynomial splits, depending on whether we take that root to be plus I or minus I. So we have an automorphism object, or automorphisms of this object. And we can restore uniqueness by considering the whole thing in slice categories. So this brings me to my definition of a stable functor, which is this universal property that whenever we have, so firstly we define a candidate, which is the generalization of a universal map, and it's such that whenever we use a candidate, so long as whenever it's in a commutative square like that, there's a unique diagonal which has to make two triangles commute, both the upper triangle in the category Y and the lower triangle in the category X. And I define a functor to be stable if every map from a Y to an S of an X factors through a candidate, and that factorization is unique because of the universal property of a candidate. So here's a dangerous bend. This definition is very similar to that for a factorization system, except that factorization systems are more special. Every factorization system gives you a stable functor, but not conversely. And the difference is that EPIs in a factorization system compose, but candidates for a stable functor don't necessarily compose. So I fell into that trap. And then applying this to something a bit more familiar to you, polynomial functor, one of that kind. In this case, the candidates select a member of the coproduct and a member of the coefficient set and the identity in this exponential, and then the factorization fills in the appropriate function like that, and then we can this construction still works if we divide those exponentials by automorphism groups on the set BI. And categories of this nature, so multi-colimits are an example of the multi-adjoints that we've been talking about. So that's a simple one that happens in the pre-order. There can also be automorphisms, and there should be an example of this for fields, but I'm afraid I've forgotten my Galois theory. Another way to see all of this is that it all happens on slices. So a stable functor is one which has a left adjoint on each slice. So a better way of thinking about the whole subject is that stable categories and functors between them are made up of their slices. And that's the reason why I propose the word laminated for any future study of this subject. And the extreme cases are what I called homomorphisms for not very good reasons, which have ordinary single left-hand adjoints in the traditional sense, and what I call isotomies, where we have an equivalence on each slice. So they're equivalent to fibrations whose fibers are groupoids. And what the theorem that I'm going to show you is that these form a factorization system. All of this is a generalization of some well-known categorical algebra, putting multi in front of everything. You're probably familiar with Gabriel-Ulmer duality between locally finitely presentable categories and left exact categories with finite limits. And then we put poly in front of all of these things. And then does a PhD in reading Dier's stuff and linking all of this up with disjunctive theories. And then, of course, the other point of view on this is so these categories are categories of models of disjunctive theories, and you might alternatively look at their classifying hypotheses for these theories. So I think there's a PhD thesis in that, unless it's already been done, and Nathaniel is the expert on that subject, I think, at least that I know of. Okay, so this I'm going to switch from the category theory to another of the contributing ideas in this subject in the 1980s, and that was well, the big project was to get what they call a fully abstract model of Plotkin's PCF, and in particular, we need to understand what a sequential algorithm is. And Gerard Berry's initial observation on this is that a sequential algorithm, if it's managed to produce a certain part of its output, it did that by using a certain minimal part of its input. Now, the way to understand that is by means of the classic non-example, and that's parallel OR, which can manage to produce you a result true even when one of its inputs is undefined. So if the inputs are true and undefined, or undefined and true, it will produce true as an output. And that's the basic non-example of a sequential algorithm. So what I've said in words is expressed in symbols as the order theoretic version of the notion of stability that I defined categorically. And well, there's some. I'm working from a useful email that Berry sent me in 1987. He went on from what might be imperative algorithms to lambda calculus. He said he had to learn what a Cartesian closed category was for this purpose. So he gave us a syntactical analysis of lambda calculus and Plotkin's PCF, made this observation about what the order between functions had to be. And this is where the name Berry order came from. He gave the semantics of PCF in terms of a certain kind of domains with the Berry order on them, which it's easier to see why this happens in the categorical way. Now I'm telling you a tiny fragment of this story about sequential functions. That I sort of only intersected with it in this much that's shown on this slide. Various other people, I think Thomas Erhard was one of the leaders of this, went on to define more complicated kinds of domains, and there were higher order examples and counterexamples, and eventually this led into game semantics, and I see that Martin Hyland is here. He's one of the major figures in getting that model, but I was not involved in that research program. So the Berry order is, and the need for the Berry order is much easier to see in categorical terms. So even if you start off with a category which has not got any interesting pullbacks in it, and you have a morphism from one category and a morphism from another category, when we form the product category, we have a pullback diagram like that. So if a functor is to preserve, is to be stable from that product category to another one, it has to preserve this pullback. So in particular, if the second one is to be an exponential object, then the evaluation map has to preserve the pullback, which we rewrite as the second square down there. So we've got a Cartesian, we've got a natural transformation phi between two functors S1 and S2, such that the naturality squares are always pullbacks. And this is called a Cartesian transformation. Now, you may know that I consider the word Cartesian to have been seriously, heavily overused in category theory. And in other circumstances, I've tried to give Cartesian things other names, but I haven't thought of another name for this one. I would encourage somebody else to think of another name so that we can retire the word Cartesian. But we're stuck with it for the moment. So then we have a program of constructing Cartesian closed categories of these things. And I need to stress again that this is a very different construction from what Sean was doing. This is a much more naive way of looking at things and looking for Cartesian closed categories. The first examples were order theoretic with domains. The one that Berry introduced were called DI domains, where so we're adopting some of the things from traditional domain theory, what are called algebraic properties in domain theory, with compact elements. And I means that the compact elements are actually finite. They only have finite many things below them in the order. And D means that the stuff below any of these compact elements is going to be a finite distributive lattice. And then Girard's qualitative domains and coherent spaces, these slices were actually Boolean algebras. So I was going to add another slide, but didn't get around to doing it, describing the coherent space model, which may be familiar to some of you in these terms, and I'm afraid I didn't do that. Now, the reason for the distributivity is in order for the function space to be boundedly complete, the slices have to be distributive. Now, these constructions are very, very simple. And Girard claims that he actually discovered linear logic by playing with the coherent space model, which is simple graph theory. So there's quite straightforward ways in which you can add graphs together or multiply a graph by another graph, and form lists of them, which he called exponentials. So he claims that that's how he discovered linear logic and the linear decomposition of functions. And then he went on to use this to model system F. And his account of that interpretation of system F in coherent spaces, you'll find in the appendix A to the book Proofs and Types, where I sort of added some of my own stuff and tried to calculate some of these things. Actually, then people then realized that the same things could be done with Scott-style domain theory as well. So returning to the category theory, we have these candidates, U from Y to Sx. And then if you have a natural transformation between two functors, S and T, when does composition with this natural transformation preserve candidates? And the answer is that it does so if and only if it's Cartesian. One direction of the proof is there. We're assuming that phi is Cartesian, and then we show that it turns S candidates into T candidates, and the converse is there so the bold square is, we're testing whether that's a pullback and assuming that this composition on the left-hand side turns S candidates into U candidates. I'll leave for you to study my slides and find out the proof yourself. Right, so this is a lemma towards the theorem that we're getting to. So I mentioned to you before about the extreme versions of stable functors, where one extreme where we have a straightforward left adjoint, and the other extreme where we have equivalences on slices, any stable functor factorizes as a composite of those two things, h followed by f. And the intermediate category, the objects are the candidates, and the morphisms are the squares that you would expect if you're familiar with the with comma categories or slice categories. The left adjoint C and the isotomy F are given as the obvious product projections from those. F is an isotomy because of the universal property of candidates. So we have two candidates with the same Y and different X's, and some morphism between them. And if they're both candidates, then that morphism H has to be an isomorphism by the universal property of candidates. Right. So then that describes how you find the right adjoint, and then the composite of the two is the given stable functor as required. Right, now for a factorization system, we need a universal property, which is filling in a diagonal map in a square like we had earlier on, but we're in a two-categorical situation. So we might have natural transformations between the two roots around the square. So the natural transformation is phi, little phi, and the theorem says there's a bijection between these things and what I call diagonals, and a diagonal consists of a functor, that's the diagonal, and natural transformations that compare these with the composites. And the way that this correspondence works is that the adjoint transpose of little alpha is the Cartesian lifting of the adjoint transpose of little phi. So this is a use of the word Cartesian, for which I proposed an alternative name, and got a lot of shall we say strong language from Jean Benabou for doing so. So I should have given people opportunity to interrupt with questions. So are we clear so far? Okay, so the interesting thing is when we factorized two stable functors via their traces, and we have a natural transformation between these two functors. What does that do with the factorization? Well, the answer is that the two triangles commute, in fact, up to equality exactly when the natural transformation between the two functors is Cartesian. And then this functor phi in this case is both an isotomy and a left adjoint, essentially because of the way that we've constructed it. And these things, functors like phi have very, very, very strong properties. So it's a rigid adjunction, that is to say, it's an internal adjunction in the two category of stable categories, stable functors and Cartesian transformations, by which I mean that the unit and the co-unit are Cartesian transformations. And then you find that every rigid adjunction is actually comonadic. And even when we've got a stable functor with a Cartesian map into the identity, so that is a co-pointing functor, that is uniquely a comonad. So you don't actually need the multiplication to define it. And we have rigid adjunctions are equivalent to functors that are left adjoint and are also isotomies. So they have very, very, very strong properties. And in the order theoretic case, like DI domains and coherent spaces, they're actually just graph embeddings of the traces. I've been running far too fast on this. So this means that it's actually quite easy to define, to study Cartesian closed categories. So, right, so the kind of categories, stable categories that I've been describing are described by their slices. Let's go back a bit, right? So if we know what the slices of X and Y are, then the slices of traces between them are obtained in fairly straightforward categorical ways from it. So in particular, if the slices are distributed lattices or toposes, then the same is true of the traces. So that means to say that the same is true of slices of function spaces. So that means to say that we have many flavors of Cartesian closed categories of stable domains, stable functors, and Cartesian transformations. And it's a bit like choosing your pizza toppings. So you can make your slices distributive lattices or Boolean algebras or toposes or Cartesian closed categories, or quite a lot of other different things. And then you might say, how numerous are we going to allow our multi-colimits to be? Now you'll appreciate that those will go up exponentially when you form function spaces. So you may want to arrange for the only to be 0 or 1 multi-colimits. And then the other thing that might happen is that these multi-colimits could have groups of automorphisms. And that's mathematically a bit more interesting than the cardinality of the spread. So there's certain classes of groups that could arise at this. Now, when I was a graduate student, my sort of side interest besides category theory was finite group theory, because I was in Cambridge at the time that the Atlas of Finite Groups was being finalized, and I went to numerous lectures by John Conway. So I had this secret hope that I might smuggle some finite group theory into category theory and theoretical computer science, and the best I managed to do with that was, I'm afraid, some permutation groups, and definitely not the monster group in that. Now, another thing we could do, this is related to the question I put to Sean in his model. So when Dana Scott started doing domain theory in the early 1970s, he constructed models of lambda calculus as limits of diagrams of domains. Well, they started off being finite, and ended up being the limit was obviously not finite. But a significant property that appeared from that is that when you have a filtered diagram or just a chain, of embedding projection pairs. So these were adjoint pairs of continuous functions. The co-limit of the embeddings is isomorphic to the limit of the projections, the left and the right adjoints respectively. And when I was doing this in my thesis and shortly afterwards, I called these things bilimits. And I didn't know at the time that the Australians had already used the word bilimit for in two-dimensional category theory. So I propose as an alternative name to that ambilimits. And I'm also responsible for the word bifinite, which derived from bilimits. So I guess ambifinite would be the replacement for that one. Now, the important thing in Scott's original work is that if we're constructing function types, well, function types in the basic categorical understanding of them are contravariant in the first argument. But if we're working with bilimits of embedding projection pairs, it becomes covariant because instead of being contravariant in the embeddings, it becomes covariant in the projection. Sorry, that's not very careful language, but you can work out what I mean with that. And the same happens with rigid junctions because we're just adopting that much of the theory. And rigid junctions also have a push-out pullback coincidence, but I'm not going to go any further with that one. So because of the limit co-limit coincidence, the category of domains and comparisons or embeddings looks like a domain. In Scott-Child domain theory, this is a two category, and we really ought to deal with the two cells. But if we did that, we'd end up with infinity categories. In the stable case, I think, well, the two cells are certainly isomorphisms rather than general maps. They might just be identities. So it might be possible to get rid of them altogether. Now, when I first heard about homotopy type theory, and in particular about the univalence axiom, I thought I've seen that before in domain theory. So I have a proposal to make to people who particularly work on, well, either work in homotopy type theory or work on models of it. How could you define domains of unrestricted H level so that there is naturally a domain of domains? Okay, so this is another project that I'm offering as a PhD thesis. Now, since we're using Scott continuity in initial objects, as in ordinary Scott domain theory, size issues are not relevant, except for the spread, that is to say, how numerous the multi-colimits can be. So it's a good idea to restrict that. Obviously, with your domain of domains, you're going to get the supremum of the spread of the things in it. So that will be unbounded. So we need to restrict to the case where the spread is 0 or 1, which, as I said, requires the slices to be distributive. All right, so this is all about your pizza toppings, right? There's some restriction on what your choices are. Now, if we've got a domain of domains, we can model Girard's system F, which has quantification over types. So this is the church numeral, so the leading example that we might want to apply this to. So we could do, so we of course generalize function types with some difficulty to dependent products. And then if we take the dependent product over the domain of domains, then we have a way of modeling quantification over types. This was done in Scott-style domain theory by Martin Hyland and Andrew Pitts at roughly the same time as Girard was doing his work on System F and linear logic and so on. I rather doubt whether they attempted to calculate what this church numeral type is. I would expect that it would be horrendously complicated, because I actually did this with coherent spaces in the appendix to Proofs and Types, and it was not nice. So calculations in the stable versions of these things were slightly more tractable than in the Scottsdale domain, but we never managed to find a model in which the search numeral type looks like anything like the actual numbers. And so that was the reason for my challenge to Sean earlier on with his model. So I'm afraid I didn't write this stuff up very well. You'll find on my webpage the better draft papers that I wrote. So I gave up on this because nobody seems to be listening to me. So then along something like 15 years later, people came back to stable functors, except they were called containers, I think. And a number of people managed to get themselves chairs on the basis of working on this, which rather, I felt rather peeved by this. And then I think it might have gone out of fashion again, and now it's gone back into fashion again. So if you find yourself in the situation where nobody seems to care what you're doing, maybe you need to find another project, but also make sure you write up your results properly, including the mistakes that you've made, because the subject may come back into fashion again, and at that point you'll finally get your credit. But there's something else to learn from this, and that's the different roles of younger and older mathematicians. And I stress that I do not consider one to be better than the other in either direction. We have this notorious quotation from Hardy saying that he basically said you'll finish when you're 40 as a mathematician. And then we have another quotation from our own community, Saunders MacLean, who said it's not a good idea to put lots of bells and whistles on your theory. What you need is the right generality. So what I did when I was younger was deliberately choose the most difficult versions of anything. And in category theory, it's easy to find very difficult things to do. What's more difficult is to judge whether you're doing the right thing, and making sure that you've got at the end of your lectures, do you have a take-home message for the audience? So this is something you learn with maturity. So younger and older mathematicians have different roles to play in this, and I'm not saying that one is better than the other. I think I've probably finished, probably gone rather faster than I should have done. So you're invited to tell me what you didn't understand in that one.
All right, thanks, Paul.
I was going to say, I thought I gave this talk as a local seminar last week and used up the whole hour. So I thought I was going to do that, but that was because there were quite a lot of interruptions. I did think that I might write more stuff about the models, the Cartesian categories and models of polymorphism that were devised at that time, but I'm afraid I didn't get them into my skull in time to write the slides. But any PhD students in search of projects, there's plenty of stuff there that could be developed.
Great. So questions from the audience? Well, there was one question in chat. It sounded like you were saying that the container story was subsumed by or the same as the stable functors story.
I'm not going to make any such allegation. I had moved on by the time containers came on. I had moved on, so I don't know exactly what I did kick myself for at that point was that I knew that Andrew Joel had called these things analytic functors, but it didn't occur to me to differentiate them.
So stable functors are the same as analytic functors, or that one is a special case of the other?
Well, I guess that they probably generalize slightly more, but analytic functors and your polynomial functors, I think, are meant to be on toposes or locally Cartesian closed categories. So I'm talking about more general categories. Mm-hmm. So in that sense, they're more general functors.
But in a topos, you think the notions might coincide?
Sort of, yes.
Can we just go back to the slide with that just has the precise definition?
With that definition, my definition of candidates and that one.
Can I say something? I think the stable functors are what many people call local right adjoints. And that's so if you restrict to pre-sheaf categories, then I think they're the same as Marcelo Fiora's pre-sheaf polynomial functors. But I'm not completely sure, but the work of Mark Webber analyzes this. And I think he's also quite good at giving Paul credit. I don't remember exactly how he compares with stable functors. But I think, for example, if you take a polynomial functor and you make the trace factorization, then the trace is just the right adjoint part. Is that right, Paul?
Yes, yes.
Okay.
Yes. But what I need to stress is that this is more interesting in which, if you're rather trivializing it if you're restricting attention to categories which have terminal objects.
Yes.
So this is more interesting when there can be many different slices and they don't add up to a terminal object.
Yes.
Right. I think so. If there is a terminal object, then local right adjoint is the same as parametric right adjoint. So maybe
yes.
more people use that. I see, Nicola.
Yeah, yes, I think that's correct.
Yes.
But the functors I was talking about last year, they are between subcategories of pre-sheaf categories that they don't have a terminal object.
Yes.
And they were modeled, yes, using your work. So
yes. So the model that you described was based on what I call my groupoids model.
Yes.
So that started by saying, well, what if we want a Cartesian closed category in which the category of sets is an object, and then we have stable functors between them, and then what's the function space? Well, the function space doesn't have a terminal object anymore, and it's a subcategory of some G sets where G is I've forgotten now, but it's probably all the permutations of finite objects.
Yes, so,
and then you look at higher function spaces, and it's not quite all of those. You have to restrict them in a certain way that we need actions of the group that are faithful up to a certain measure, which I call the creed, and Marcelo's model that he described last year was an elaboration of that idea, I think.
Yes, that's correct. It is also joint work with Hugo Paquet and Zainab Galal, and what we were doing is taking your work further to get a model of classical linear logic with differential structure as well.
Yes.
In the line of species of structures. So.
Yes. Okay.
Would we be able to see the simplest non-trivial example of a stable functor?
Well, we've just been discussing that. I mean, if you're working on in a category with a terminal object, like sets or a topos or locally Cartesian closed, then it's the same thing as a polynomial functor. But when we have categories that don't have terminal objects, there can be different things happening on different slices.
So can we see an example when one of, like, field, for example, is one of the categories involved?
Yes. What makes fields not as interesting as it might be is that all the morphisms are monomorphisms. So the slices are all complete lattices. So we would need somebody with more knowledge of commutative algebra to get some more interesting categories of that kind.
Okay, thanks. And it looks like Nicola might have a question.
Yeah, well, first of all, thank you, Paul. I thought it was very nice to put things in historical context, and it was really lovely to hear it from you. Can I just ask in this vein, there seems to be this work of Dia in more algebra type of setting, and then this jump towards computer science. So who was responsible for bringing those ideas towards computer science? Maybe you, I don't know.
Well, it was probably me and Francois, I would guess. I mean, Yves Diaz was a regular attender at the peripatetic seminar of Sieves and Logic. He was based in I've forgotten the name of the place. It begins with a V, and it's near the English Channel. Valenciennes, is that right?
I don't know.
No, he was definitely interested in commutative algebra rather than computer science. Now, Francois was in McGill. He's Quebecois. He was in McGill, where he got his influences from. I'm not quite sure, and I'm not sure. I don't want to speak on his behalf. Now, whether Girard knew anything about Diaz, I don't know. Girard certainly knew about Berry. There's also Girard's dilators, which are another example of this, but I don't understand what dilators were for. I'd quite like somebody to tell me that. And Peter Johnson had papers commenting on these subjects as well. Joachim had a very interesting diagram of the relationships of papers and how they influenced each other, which I think is a bit out of date. It would be good if you could, you and other with the help of other people, could bring that diagram up to date and publish it, I can give you my collection of references from the 1980s, and other people would contribute from other decades.
Thank you.
And so I had a question actually. So yesterday, somebody in the chat asked about relationship with Girard's analytic functors. Maybe you can comment on that.
You need to remind me what he meant.
Something he was trying to make a model for the lambda calculus somehow. And
well, he had something called quantitative domains. So I changed quite a lot of what Girard did. So I'm not very. I don't remember what the original version was.
But this was in the context of Christine's talks, right? No.
The question was yes, but I think
yes, but
only because of the name of analytic functors.
Yeah, so I think there was no connection with the talk.
Analytic functor was, as I understand it, Andrew Joyol's term for the polynomial.
Girard had normal functors, which are very close, but not quite the same.
Normal.
Right.
Yeah.
Well, maybe now's a good time to stop and thank Paul again.
Thank you again to Joachim and David for organising this and inviting me and putting up with my troublesome audio on my laptop.
Our pleasure.